I think we can start right on time. In the back, please give me a signal if you can't hear well. If volume is good. Okay, wonderful. So my name is Ilka. I'll be the chairperson of today, and I'd like to wish a very warm welcome to everyone for Shubhangi Bhadoria's doctoral defense. So first of all, warm welcome to Shubhangi. You've been with the division since I think 2020.
Yes.
When you started as a PhD student, and today we're very excited to hear everything about enabling short-term overcurrent capability for silicon carbide power modules and its application for power flow controllers in HVDC grids. I'd also like to welcome our opponent, Dimosthenis from NTNU Trondheim. Very warm welcome. And I would like to welcome the members of the evaluation committee. And as is custom here, we start with the university with the longest distance. And I checked this morning, actually, that would be Chalmers in Gothenburg. Warm welcome to Professor Torbjörn Thiringer. And then similar distance, but a bit closer to KTH. Warm welcome to Professor Kent Bertilsson from Mittuniversitetet in Sundsvall. And then finally, warm welcome to Professor Cecilia Boström from Uppsala University. I'd like to extend the welcome also to the supervisor, Hans-Peter Ney, and the stand-in member for the committee, Hans Edin. And I think we can keep it short here. And I'd like to give the floor to Shubhangi to present her work in the last 5 years. Thank you.
Okay, so hello everyone. Can you hear me at the back? And the volume is okay. Perfect. So let's begin. So as Ilka introduced, first of all, thank you, Ilka, for introducing everything. So the topic of my PhD thesis is enabling short-term overcurrent capability for SiC, which is silicon carbide power modules, and its application for power flow controllers in HVDC grids. So there is a printing mistake on page 21 in the thesis. So the melting point of LM108 is 108 degrees centigrade, not 180. I somehow flipped these two digits while typing. And the rest, let's begin with the presentation. So this is the table of contents I'll be presenting today. First, I will talk briefly about motivation and background behind the project. And then I'll present thesis outline, and I'll talk in the same sequence of original contribution as I wrote in my PhD thesis, from original contribution 1 to 9. And then I will conclude, I will give conclusion and future work for overcurrent capability research aspect and power flow controllers for HVDC. So the motivation and background, as we know that power electronics application is everywhere, from almost everything to everything, starting from your, for instance, your electric toothbrush to your hair dryer to more sophisticated applications such as solar, satellite, even your mobile chargers and EV. So we can see here that we have the need of power electronics everywhere. However, my work would be focusing a bit more on the power system, and the discussion will go on in the same context from now onwards. So a surge of overcurrent can arise due to faults in transmission line, faults in equipments, cyber attacks, oscillations due to transients, and there might be many more reasons. And then the fault clearance time in the power system can vary from a few milliseconds to few hundreds of milliseconds, typically until 10 cycles. And then I will talk about the enabled overcurrent capability of these devices. How they may be useful for power flow controllers in HVDC grid. So the thesis outline is as follows. First part consists of the technologies or techniques for enabling overcurrent capability in silicon carbide MOSFETs or silicon carbide devices in general. And then the second part will focus more on the application of power flow controllers. I will be using OC for overcurrent sometimes and PFC for power flow. And that's how the outline of the thesis look like. The same thing I just said. And then, because we have electrical engineers who are not maybe from power electronics, this slide is for them specifically. So you might have seen this converter in a lot of textbooks. So any any switch you see here would be like this in the reality. So this is the chip, semiconductor chip. Then we have ceramics for basically dissipating the heat towards, for sending the heat from chip to further in the power module. And then we may or may not have base plate depending on the power module design, and then the heat sink, and then there is an encapsulation to protect it from environmental aberrations or other external factors. So that's how your simple switch can look like inside the power module, basically. And then first, I will talk about the original contribution one, in which I investigated various techniques of overcurrent. So I did the investigation for the problematic locations inside a power module. I focused mainly on the aspects for the temperature greater than 200 degrees centigrade. And then these were the locations which may have the issues during the overcurrent. That include chip itself, metallization over the chip, bonding techniques, substrate, die attach, encapsulation material. And then the techniques to actually remove the heat or to reduce this thermal stress include application of heat-absorbing materials. I'll talk more in detail about these. Could be microchannel cooling, control and modulation techniques, and paralleling the modules. And then I did the thermal analysis for various phase change materials and sensible materials. For the people for whom this phase change material is new, is any heat-absorbing material which changes its physical state upon absorption of heat. Of course, we choose the melting point in such a way that we can use the latent heat of that material. So this is phase change. And second is sensible materials. These materials will not change their physical state when we use it for our application. That include metals, diamonds, graphite, because they have melting point much higher than the operating temperature. And then the way I investigated these materials is as follows. This is a semiconductor chip, and we are assuming a heat-absorbing material on top, and the top surface is adiabatic, and the thermal or the heat flow for this material would look something like this. Heat is coming from down. And then I assumed initial temperature to be 100 degrees centigrade before applying the power. And then upper limit in this investigation and until the end of this presentation is 250 degrees centigrade for silicon-carbide devices. And then power here, I assumed 400 watts per centimeter square for a futuristic chip of silicon-carbide of 1 by 1 centimeter square area. And I did analytical calculations and COMSOL simulations to investigate the same for the time range of 200 milliseconds, as it says in the title, short term. So that's what I've been focusing on here. And then this was the list of whole materials which I investigated for heat absorbing application or as a heat absorbing material. So from here to here, these are all phase change materials. As you can see, they have very high specific heat, but they have very bad thermal conductivity. On the other hand, metals here, so at the bottom of the table, you will see the metals, copper, silver, gold, aluminum, and nickel, and diamond. So they have very high thermal conductivity as compared to higher thermal conductivity as compared to these phase change materials. So for absorbing the heat, the expected graphs are as follows. For copper, we can see for 200 millisecond time range, the copper is actually able to keep the temperature within the desired limit. And this red curve here shows the temperature of the chip or the temperature temperature of the surface closer to the chip. And the green one shows if the material has infinite thermal conductivity. So we can see that the copper is able to basically keep the temperature below 250 degrees centigrade. For the phase change material here, this is the one I investigated. We can see that if we have just the material directly, it will increase, the temperature will increase suddenly to the limits which definitely we don't want in our semiconductor devices. So we can see that the metals and furthermore materials like diamonds, graphite, they will have application in the range of few milliseconds. So I will consider only the metals and diamond and graphite from now on for this investigation. So this is the table which gives an idea for two time ranges, first 200 milliseconds and then second range. So let's focus first here. I did the same investigation for the copper, which I just showed. Similarly, we can do the investigation for rest of the materials, and this is the height corresponding to every material and the mass corresponding to that particular height. And of course, the diamond. I'm mentioning diamond separately because it has different electrical properties as compared to the metals. And then I kept on increasing the height and checked the limit, how long can I actually increase the overcurrent duration. So I kept on increasing, clamped the temperature at 250, so on and so forth. And the maximum possible duration with these materials for the time, maximum duration for these materials with the same dimension and the same power are as follows. And the height corresponding to these materials are here, and the corresponding masses for these heights. This is the same information in graphical form for 200 milliseconds. As we can see that the copper is among the elements which is among the metals which has lowest masses, and it's of course cheaper as well as compared to other metals here. And then this is the same graph for corresponding to this. So how we can read this graph is as follows. So for example, first let's talk about copper. So for copper, the maximum possible overcurrent duration for this particular arrangement is 1.5 seconds. And the mass required is approximately 20, or it's about 17.9 precisely. Similarly, the maximum overcurrent duration possible with diamond is around this much. It's 5.1 here. That's how we should read this graph. One thing, as we can see that the copper, among the metals, copper has the highest overcurrent duration, and diamond has highest duration, but we can see how much of diamond we need. It's more than 50 grams. And the key outcomes of this investigations are as follows. So we were able to identify the locations where we may need some techniques of cooling during the overcurrent. These are the ones marked in green. And then this is another graph indicating the conclusion of everything. So how to read this graph is as follows. If you want the heat absorption in millisecond range, for example, this one from nanosecond to hours, millisecond range, we should be concentrating more on metal, diamond, graphene, so on and so forth. And if we want the overcurrent duration in second range, then we should be focusing on phase change material, maybe not the ones which I showed, some other which we will discuss further as well. And if you want the modification of the power module characteristics on the nanoscale, so I would say just change the layout altogether starting from the die. So that's how, that was the conclusion of this investigation. And then metals and diamonds are best for overcurrent application due to their higher thermal conductivity. Active methods all include Peltier and microchannel cooling. I will be discussing microchannel cooling in detail in the further slides. Here, active methods mean it needs some external, either a pump or a current source, for example, for Peltier. And then let's continue for original contribution 2, in which I tested silicon-carbide MOSFETs from onsemi rated for 30 amps. For various overcurrent cycles of 1 milliseconds. I tested them for 2 times overcurrent to 5 times overcurrent using an SC oscillatory circuit like this. However, we have used a diode so that we have only 1 pulse when the capacitor discharges through the inductor. And the T pulse for this particular arrangement can be given by pi root LC, and the IP can be given by under root C by L dot VC. This is for ideal circuit, of course. And then this is the picture from the lab in which we tested these devices. So as I said, rated current was 30 amps for these 20 devices were tested for each overcurrent for 50 cycles and 100 cycles. And these devices were characterized by the curve tracer before and after the tests. And then that's how the power curve and the current and voltage curves look like. Here we can see that the devices failed at the end of the cycle for 5 times overcurrent, and gate and source terminals got shorted at the end of this cycle. The outcomes for this investigation are as follows. First, we estimated the junction temperature for different overcurrents from 2 times overcurrent to 5 overcurrents, and this is the estimated junction temperature or the chip temperature. We can see that until 4 times overcurrent, it's 178, which for silicon carbide is not an issue as long as the packaging doesn't create any problem or hindrance. And then from 4.5 OC onwards, it's 305, 636, and 782 degrees centigrade. So other observations are as follows. The devices for 4.8 times overcurrent failed anywhere between from first cycle to 10 cycles, while all the devices failed in the first cycle for 5 times of overcurrent. RDS-on during these tests didn't really increase much. It typically stayed for less than 3%. However, the increment in VTH threshold voltage was increased by 3.5 and 4.3% after 50 and 100 cycles for 4.5 times of overcurrent. Then let's continue for the next original contribution. In this one, we did the comparison of copper versus phase change plus copper block. How it looks like? Let's see. First of all, this LM108, which I mentioned in the beginning as well, it's a synthetic liquid metal, and it's an alloy, and it's tuned for obtaining the melting point of 108 degrees centigrade. And then another phase change material which I will be using is lithium metal. It's a typical lithium from periodic table with atomic number 3, and melting point for this is 180 degrees centigrade. So I investigated 3 power module designs. First is the standard power modules, what I showed previously. Second one is a modified power module, in which we have a big copper block below the chip. And then we have another one with the same dimension, but it has phase change materials, phase change material inside these 4 holes. And then I did the comparison for silicon and silicon carbide devices. The phase change material for silicon is LM108, and for silicon carbides, it's lithium because its melting point is 180. And the maximum temperature for these investigation for silicon was 175 degrees centigrade, and for silicon carbide, it's 258 degrees centigrade. I will show only the cases for silicon carbide here because the investigation gives roughly the similar outcomes with the same logic flow. And I will present the DC-DC, I will present its application for DC-DC converter, which is operating at a duty of 50% with a switching frequency of 7.5 kilohertz. And this is the table for the losses during various overcurrents here from nominal overcurrent, from the nominal current to 4 times overcurrent. And then key outcomes are very interesting, actually. So the first one for 2 times overcurrent. In all the graphs, red curve shows the temperature response of the power module, of the chip, actually, for the standard module. And then the black curve will show the copper plus phase change, and the gray will show copper, the response only with the copper. So for 2 times overcurrent, we can see there is a significant increment in the overcurrent duration. Overcurrent duration here, I will be referring as the duration in which the chip attains an average temperature of 250 degrees centigrade. So that's how we should be reading these graphs. So we can see that it's increased from around 0.75 seconds to roughly 5 seconds here. Similar observations are made for 3OC, however, the time scales are in few milliseconds or a fraction of a second because the power is higher and the temperature increases faster. In this case, you can see that copper plus PCM has shorter duration than the one with the copper. And then it has similar response for both the power modules with just copper block and copper plus phase change for 4 times OC. And then the amount of phase change material melted looks like this for 2OC, because it's a slow heat absorption as shown here and the slow increment of temperature. The phase change material was able to melt until 70% for 2 times overcurrent. For 3OC, as we can see that it's somewhat less than 200 milliseconds, and it's a very short amount of time for phase change material to melt because of its low thermal conductivity. So it melted maybe 0.5% or hardly 1%. And for 4OC, it's a flat straight line, no melting, because it's really in tens of milliseconds here. This is the summary of what is shown here in the graphs. We can see for 2OC, it increases from 0.75 seconds to almost 5 seconds. Then for 3OC, it increased from 30 milliseconds to 210 milliseconds with copper, and with copper plus phase change to 120. For 4OC, it increased by 2 times, but since these are very fast transients and power is really too much during 4 times overcurrent. So the key outcomes are as follows. As we have seen in the graphs and in the table, that we achieved similar performance for PCM plus copper and copper block for silicon carbide power module. Then, however, as we have seen this, for incorporating phase change material, we need some more sophisticated manufacturing. And then similar outcomes were observed for other cases, which are present in detail in the thesis and in the papers at the end of the thesis. So next original contribution is about the comparison of top and bottom cooling for overcurrent, in which I investigated four designs of power module. First is standard power module without any modification. First is the one in which we have heat absorbing material on the top of the chip. And then for the third one, we have the heat absorbing material on the bottom of the chip. And for the fourth one, we have it on both the sides, top and bottom. So the results for this are also very interesting because personally I was hoping that this will have the best performance, but you will see what happens. So the comparison was done between among these 4 arrangements, and then this is the equivalent thermal circuit, or let's say the power flow during the steady state. For the standard modules, RSTD is the standard is the thermal resistance for standard modules. For the bottom, it's in the path towards heat sink. For the top, it's in parallel with the heat sink, and for top and bottom, it's, let's say, the combination of both. Then the heat flow, whenever we have top cooling, for instance, in this one and in the last arrangement, there would be a heat flow or flow of heat on the top. Then materials I investigated for this one as a heat absorbing materials are copper, graphite, and aluminium. Heights I varied from 1.6 mm to 20 mm. For graphite, I increased a bit more. We will see why. So the performance with the copper is as follows for 2 times overcurrent. First one shows the copper at bottom, copper at top, and it's copper plus top plus bottom. So the solid red curve always represents the performance with the standard modules in all the graphs. Any variant of the curve in red or any variant of red color shows that it is the overcurrent duration is less than the standard module. And all the green and green variants show here that the overcurrent duration is more than standard module. And if you see blue curve in any of the graphs, which means it has similar overcurrent duration as that of the standard module. So here we can see that as the height increases, the steady state temperature for bottom case will increase. And then the overcurrent duration, of course, it's less than the standard module, but still, it first increases and then it starts decreasing. We will see in the table for more clear numbers. And then for the top case, it keeps on increasing as you increase the height of the material on the top. We kept the same area as that of the chip. So the overcurrent duration keeps on increasing. However, the rate of increment of overcurrent duration decreases as we go further in the height. And then the temperature is somewhere in between these 2 graphs for the top plus bottom, because it has first an obstructed flow towards the heatsink, and but still there is some cooling on the top of the chip. Similar observations are made for 3 times overcurrent. However, for the copper at the bottom, there were some heights, so 1.6, 2, and 5, for which it increases, and then it starts decreasing because of the increased thermal resistance towards the heatsink. And then overcurrent duration keeps on increasing for the top, and similar observations are made for 3 times overcurrent. The similar observations with the same logic flow and in the similar sequence are observed for graphite, for bottom, top, and top plus bottom, for 2 times overcurrent, 3 times of overcurrents. And the summary is as follows. So this is a table which summarizes the overcurrent duration for different arrangement for different overcurrents. So we can see here, let's concentrate on this column here. First, the overcurrent duration increases as we increase the height because we have more material available on the top. It first increases, for the bottom case, it first increases and then starts decreasing. Similarly, for top plus bottom, it first increases and then starts decreasing. Similar observations are made for 3 times of overcurrent. However, the durations are different because of the different power increased in these 2 different overcurrent phenomena. Similar observations are made for graphite. You can see that the durations are increasing as we increase the material. I investigated this until 100 because I wanted to see how much can we actually gain from graphite. And the similar trend first increases and then decreases was noticed for bottom and top plus bottom for the graphite as well. One interesting thing to make an easy comparison is this. For the top case with copper for 2 times overcurrent, for example, the duration is 6 seconds. For graphite top with the same overcurrent duration, it's 3.3 seconds. As we know that the graphite has 4 times more thermal conductivity than copper, then I was, at least in the beginning, was surprised to see why is it less than copper. The reason is because of the low mass density of the graphite. So we have the way to take the heat out, but we don't have the, let's say, a container to keep the heat. So this was the reason that this duration was slightly shorter. Not slightly, actually, much shorter with the graphite as compared to copper. And then the key outcomes of these investigations are, first, top cooling is best in terms of steady state temperature and overcurrent durations. Bottom cooling is the worst for the same dimensions. Bottom cooling can achieve a similar performance if it is implemented below the chip, but with a huge block of copper, for example, the way we investigated in the previous original contributions. And then after this investigation, we recommend a maximum height of 20 mm due to otherwise the parasitic inductance might increase in the system too. Then application of graphite is toughest because of its powdery nature and this slippery surfaces. However, there are a few techniques mentioned in the literature such as electroplating and cold spraying. Then let's talk about the microchannel cooling here. So this is the first arrangement of power module with chip and microchannel block at the bottom of the chip. So between the chip and the ceramic. And the heat flow for this microchannel block would be from top to bottom. Then similarly for the top cooling, for the top, the microchannel block is on the top of the chip and the heat flow would be from below the chip. And if you want to go into the details of the thermal resistance calculation, these are given in the paper and that's how we can estimate. So this R conduction is the thermal resistance because of these two plates on the top and bottom. R heat is the resistance caused by the heating of water. And R convection is the resistance because of the convection when the water is flowing in the microchannels. And then microchannels I investigated are 5, 10, and 15. Microchannels are made of copper. We used deionized water as coolant, and the flow rates we investigated are 0.31 and 1.73 milliliter per second. And for this one, we will only need a few, we will need a micropump of few milliwatts. We investigated this in COMSOL multiphysics software. This flow rate has already been achieved by a research group in EPFL. So that's why we took these assumptions from. That's where we took the assumptions from. And then we turned on this microchannel flow only during the overcurrents, because we wanted to reduce the temperature swing during the overcurrents and hence the thermal stresses. So the outcome is as expected. So first, let's compare, let's first see how the bottom cooling looks like. So for example, this is the standard duration in the rad. And when we check with the same amount of microchannel, the duration increases with the increase in flow rate of the liquid. Similarly, for the same flow rate, if we have different microchannels, the duration increases with the increase in microchannels as well. The similar observations are made for top cooling. However, when we compare case to case for top and bottom, top cooling has always better performance in terms of overcurrent duration as well as the steady state temperature during the steady state. And this was the conclusion here. So durations are longer with the top cooling. Steady state temperature would be lower with top cooling again. A micropump is needed. Yeah, this is what I already mentioned. Microchannel cooling is done only during overcurrents to reduce the temperature swings. Then, so far we have discussed the methods which need modification in the power module design. However, there is one investigation as well in which we don't need to modify the power module design. It's called gate voltage augmentation. As we know that the RDS1 increases with the increase in gate voltage, and the conduction losses can be lowered or kept constant during the overcurrent event by implementing this method. Further, if needed, switching losses can be decreased by decreasing the switching frequency. I did the investigation for, again, on-semi devices whose rated current was 30 amps. And here's the table for what I noticed. I varied the gate voltage from 20 to 50 volts. As you can see, it's much higher than the recommended range. And then we measured the RDS-on, and that's how it was. And we measured the RDS-on for different gate voltages. This is the percentage decrement as compared to the RDS-on at 20 volts. And then I investigated two methods in LT-SPICE. These are called three-terminal model. One is called three-terminal model, other is called five-terminal model. These are, for the first model, they assume there is no self-heating of the devices. And for five-terminal model, they assume there is a self-heating of the devices. And they are publicly available by the manufacturers. So I measured them using this LT-SPICE, and that's what I observed. And the difference from the experimentally measured values in percentage is shown here. Similarly, for five-terminal model is shown here. As we can see that it's very close to, they're very close to the experimental values, and we can actually use these models, which are publicly available, to see how much gate voltage we can increase. And then this is the same information in graphical form. By the way, at 50 gate voltage, the devices, the device was basically, there was a permanent damage to the device, and all the terminals were shorted, and there was a clicking sound. And that's how that's how they look like. The red one shows the RDS-on measured experimentally, then 5-terminal and 3-terminal model, 3-terminal and 5-terminal. So I also calculated the conduction losses for ID is equals to 20 amps, and with varying gate voltages, we can see that there is a decrement in the RDS-on as we increase the gate voltages. So we have a proposal for a gate driver. It's not a very sophisticated, so let's first discuss this. So this is the gate driver, which we have commercially available, commonly available, which supplies the voltage for turn on and turn off. However, here is one additional unit in which we can occasionally increase the gate voltage by having one measurement, VDS or on-state voltage. So according to the measurement of this VDS on, this switch can be turned on and off, similar exactly in the same way as it's done for desaturation in the currently existing gate drivers. So this will operate only and only if the overcurrent is there. Yeah. And then one question may arise, why don't we keep the gate voltage high continuously? Because it gives lower RDS on. So first of all, manufacturer provides a maximum of VGS. And secondly, continuously increased gate voltage will lead to the aging of the gate oxide, accelerated aging of the gate oxide. And then if we have short circuit inside the converter, and if the VGS on is already high, then we might have difficulty in protecting the device because the voltage will not be increased that much across the drain source. And then last point is that if we increase the gate voltage occasionally, then we may or may not we may or may not age the devices so much if it's, let's say, 1 time a year or so. Then let's move on to the power flow topic. So this is in the original contribution 7. Here I investigated various topologies and did some simulations as well. So application of overcurrent for power flow controller here, PFC or power flow controller may be needed to modify the current distribution in the HVDC system for efficient and optimum use of existing infrastructure, loss optimization, increasing profit by scheduling and rerouting the power flow. And ways to change the current distribution in any HVDC grid are, first, resistance modification, series resistance in the lines. Second is we can connect a converter by taking the power from AC grid. And third is we have a converter connected between the 2 lines. One can call it an interline power flow controller. And as we can see, they don't really need an external power supply for their operation. System under consideration is a 3-terminal system. I took this system from already published literature here. And these are the line parameters in terms of length, inductance, and resistance. The power at these 2 nodes are P1 and P2, which are 160-80 megawatts. And voltage during the normal operation is capped at 150 kilovolts. And I may be calling it slack node interchangeably. So the application of PFC is as follows. First, we have the system. And then second, if we have a PFC on the node 3, the resulting configuration will look like that it will result in the change of voltage. The direction could be any, we will see further, but that's how it will look like. It will result in the changing of DC voltage and hence the current or power. So the categorization of topologies have been done on the basis of various parameters. I investigated the topologies existing already in the literature. So the first categorization is on the basis of how many capacitors we have in the topology. First category is the category with 1 capacitor. In all the topologies, we can see there is only 1 capacitor, which will be switched between 2 lines to insert the voltage. And first of all, this is very simple topology depending on the switching. And then the rest of the topology will also do the same thing, except that some could be bidirectional. And at the end, in all the topologies, it's the capacitor which is being switched on and switched from between the 2 lines. Second one is the two capacitor topologies. These are all the topologies work in the similar fashion. And then third category is based on MMC-based blocks. And then the other criteria of categorization are the control range. This is the Vx and Vy. These are the voltages which can be inserted in these lines. And the topologies from 1 to 12, except 8, have full range of voltage control, and topology 8 has only this one. By the way, this curve, complete curve, is a characteristic equation of the HVDC system. It doesn't depend on the PFC topology. And it can be completely given by the set of equations given in the publication 5. Yes, given in the publication 5. And then the choice of transmission lines. So these topologies can be, the one which we saw in the picture, there were only 2 lines which can be, in which we can modify the voltage. However, in some of the topologies, by using the right switching or control mechanism, we can choose which lines we want to modify the voltage into. And then the shape of inserted voltage. This is one of the most interesting things of these topologies. So for the one capacitor topologies, as I said, the same capacitor will be switched between the 2 lines. So the effective or the voltage waveforms being inserted on these lines would be like this. This square wave, first there is a capacitor, and then it's not, there is one, there is not. Similarly for the other line. However, the capacitor voltage itself would look like this. But the effective voltage which the transmission lines will see are square waveforms. However, for 2 capacitor topologies, these waveforms will look like this, because there are 2 capacitors which will be charging and discharging depending on the switching of the converter. And these are triangular waveforms with a very small voltage ripple. So the transmission line will see the ripple of, let's say, in this particular case, of about 20 or less than 20 volts. So the waveforms, as we can see, are better with the 2 capacitor topologies. There is a very small ripple voltage being inserted in the lines, and hence the power quality and the voltage will not be changing the shape. And also, this ripple can even further be modified depending on the requirement. If you have high capacitance, then the ripple would be even shorter. Then the derivative of the slope of the inserted voltages for these 2 investigations are different. Here it's a sudden increment in the voltage, and here it's a gradual increment in the slope of the voltage. So due to this reason, triangular voltage waveforms are better, and they are less stressful for the cable insulation, and hence because this ripple is small, and hence the power quality would be better in terms of THD and so on. Other criteria continues as follows. The current range, the current varies according to Vx and Vy as follows. And then this is the last categorization. It's the easiness of the protection of PFC. So here I pointed out the switches or the branches which we can just switch off. And we don't need to discharge the capacitor, and the PFC will be bypassed via these switches. So the comparison of all topologies in terms of various parameters is given in this table in terms of number of components conducting at the same time, total number of components, directionality of the topology, total semi-power conductor rating, losses, and the complexity of protection. Main takeaway are as follows. The losses so in terms of losses, the losses are least for this topology and maximum for this topologies, as we can expect that there are so many switches in which the current is flowing, and hence we have more losses. Second is semi-power conductor rating. It's the least with this topology and maximum for this topology. These 2 things are somehow not the direct relation, but somehow related to the number of switches and also the amount of current flowing through them. And then the directionality depends on the switch's direction. I'd like to add one thing for this publication. We have received a revision of the paper. I received it last Friday, so I will be revising it soon. And for the next original contribution 8, we investigated what is the optimum location or the best location for PFC. We took this we took this topology from this literature again and placed it at 3 different nodes. This is the one where I showed the maximum time, showed it for the maximum times. And then I kept it at node 1, node 2. This is the result of the investigation. So in the blue one all the blue curves here show the maximum possible current variation at node 3. The yellow one shows at node 1, and the original one shows at node 2. We can see that the maximum variation of current is possible when the PFC is applied at slack node with a fixed voltage. So that's how we can choose if we really have the choice in a meshed HVDC system. Then original contribution 9, this is about proposing 2 topologies. However, they are fundamentally the same topologies. The only difference is the connection of diodes and switches. These 2 topologies are the literally inverted topologies to each other. We will be focusing more on this topology in the further slides. This is the whole range, which I said was the characteristic curve for the system. So this topology has application in this quadrant. This topology has application in the first quadrant. We can choose depending on how the power flow in the system looks like. So the specification about these topologies are these are simplest, cheapest, the expected losses are low. However, they have limited performance in terms of being limited in one quadrant. However, it may be enough for the applications where we have well-defined power flow before the PFC application, could be wind farms as well. And then I investigated these fault cases, 6 fault cases, in which 2 of them are the ground faults on these 2 lines, on the left or line 2, on the right or line 3, and then open and short-circuited diodes and switches. So the PFC quantities I will be talking would be the voltages inserted in these 2 lines and the current flowing through the inductor. So Vx and Vy and IL. So for example, in this one, when we have fault in the midpoint of line 2 or the left cable in the HVDC system, we can see that there is a constant oscillations of Vx and Vy. However, they are increased to a value which is much more than the recommended level. And also the inductor current is also increasing more than the rated one. And then on the right side cable, the waveforms look like this. But the interesting thing to notice in all these cases is as follows. In this one, we can see that these are the oscillations, and the Vx and Vy are actually passing through zero crossing. And that is the point where we can actually bypass the PFC, because we have 2 capacitors, and the capacitors should only be bypassed when they are completely discharged or almost discharged. However, in this case, we can see that this Vx is not passing through zero crossing. However, Vy is passing through zero crossing. This point would be very interesting for the proposal of the protection circuit for these different fault cases. That's how the protection circuits look like. For the first one, as I said, these both are passing through the zero crossing, and hence they can be directly bypassed using these thyristor when they cross or when they are discharged. For the fault at the right cable, we can see that Vx is increasing, so we need something here, an inductor, to discharge the capacitor. And then after discharging, we can bypass it by this thyristor, and the other way, and we can directly bypass when it crosses zero for the other side. Similar logic for other curves, and we will need the inductor whenever it's not crossing zero volt. That's how we can investigate these protection circuits. And then with the application of protection circuit, the waveforms look like this. So we can see that for most of the cases, the voltages are within the recommended range, and we are able to discharge the capacitors to 0 volt and hence bypass them using those thyristors. However, for the fault at the right cable, we can see that we are able to discharge the capacitor, but it is still going beyond the recommended limit. So this is the most severe case, and in order to design the PFC, we may have to design very carefully the capacitors of this PFC topology, depending on how the curve looks like. Yeah, and I will come back to that later, but there is a way that we can actually reduce these peaks of these capacitor voltages. We will come back to that at the end. And then I tested the same thing in the laboratory for after simplifying the HVDC system. So this is the simplified full-scale HVDC system. In the lab, I tested it as follows. 2 lines here. This is the PFC. This is used to create a fault here, and this is used to bypass the capacitor. I showed that the capacitor can be discharged and hence can be bypassed. So I downscaled the circuit, the full-scale model, to the base values of 250 volts and 6 amps. The full-scale base values were 150 kV and 1.6 kiloamps. I performed the experiments at 80 volts. And with these assumptions that SCR is infinity, arm inductance of MMC at node 0.06, and transformer leakage inductance of 0.12, the current limits during the faults are set to 6 times for the simulations as well as for the experiments. This is the setup we have in the lab. As we can see, we have the inductors here. This is the PFC, these capacitor, inductor of PFC, diode, and the MOSFET here, just above the gate driver, and the other line here on the right side. So the comparison of the experiments and the simulation. So this is a full-scale response. This is the response for full-scale, Vx and Vy, and inductor current here. Then this is a simplified full-scale. It was just to show that even after simplification, the dynamics remain the same. And then this is the result for the investigation done in the lab. We can see that they look very similar. I'll also show how they are in terms of per unit. And then after the protection circuit was implemented, we were able to discharge the capacitor to 0 volt. Here you can see for Vy, it's almost 0.9, minus 0.9-ish. It's because of the on-state resistance of the diode and the switches. Per unit comparison of all these quantities is as follows. We can see that the experimental values align closely with the simulations in terms of their corresponding per unit. And we were able to show that the simulations match the reality, and we can actually protect during the fault cases. So this was the takeaway of all these slides. And then, as I said, for the right side, for the fault on the right cable, this was the worst case in terms of capacitor voltage reaching those half sinusoid kind of curves, if you see. So we investigated how this inductor would actually change those capacitor voltages. Let's see. So this is the here in this one I made the fault in the simulations at a distance from 1/4 from the slack node or node 3, at a distance of half, and 3/4 from the node 4. And then we can see Vx and Vy, the corresponding capacitor voltages, as we come closer to the node, the severity of the fault increases for both the capacitors. And then the variation of inductance is shown here. Here I varied the value of inductance from 1e 10 to the power minus 8, 1 into 10 to the power minus 8 to 1e minus 2. We can see that as the value of inductance increases, the peak of this voltage curve increases. Also, the time to cross the 0 increases. The reason is that the higher the inductance, the higher it will actually resist the change in the current passing through it. We may think that it's bad to have higher voltages in these capacitors, but then we should also be able to comment that is our protection circuit, can our protection circuit really respond within, let's say, 2 milliseconds? So this is like a trade-off between the time to respond and the peak voltages in the capacitor. So, and this was the worst case at 1/4, and I did the same investigation for the fault at half the distance from node 3 and 3/4. As we can see, the peak of the voltages here reduces as we go further away, and this was observed for both the cases. And then, closer the fault to the slack node, the more severe the fault is. And then another interesting aspect is the current passing through that inductor, the inductor in the protection circuit. As we can see, as the value of inductance increases, the peak of the current decreases. The same logic, the higher the inductance, the more it will kind of resist. And of course, it will take more time as well. So this graph is for the worst case when the fault is at 1/4 distance, and peak of this current passing through the switch, which inserts the inductor, decreases with the increase in LP, and for this particular fault at 1/4, the recommendation of 5e to the power minus 6 Henry can be made, in which the peak current is 97 kiloamps, and there is a thyristor available from Hitachi, which can withstand such peak currents. And for the other cases, the peak current would be lower. So I didn't show this one here. So the conclusion and future work for the technologies for overcurrent. So the conclusion are as follows. So I discussed briefly the technologies for enabling overcurrent capability, and we can choose depending on various factors. I also showed the comparison of top and bottom cooling, in which cooling on the top is the best in terms of overcurrent duration and the steady state temperature. However, the top cooling may require special arrangement because we have bond wires on the top of the chip. If we can afford the complexities, such as a small pump for microchannel, then we can actually choose microchannel. So it depends on how complex we want to make the system, and we can choose the technology according to that. Could be microchannel, PCM plus copper, or just copper block rather. And then we can also choose the technology according to the overcurrent duration required. Since microchannel, for instance, had the highest cooling duration or the highest overcurrent duration, as I showed, among all these investigated techniques. And I also proposed a method which didn't need the modification in the power module, and it's called gate voltage augmentation and reduction of switching frequency. Future work includes practical implementation of the suggested techniques, comparison of top and bottom cooling with the proposed techniques in the lab, and implementation of the gate driver with gate voltage feature. And the last, what happens if, let's say, we have an overcurrent and the gate voltage is already high, and we have now the short circuits inside the converter. So this would also be an interesting investigation because we don't know how it's going to behave and how the such VSAT can react, or can we switch off this device. So these are the aspects for future work. And then conclusion and future work for power flow controllers. So first, the conclusion are as follows. Investigation of PFC for HVDC. I showed various topologies. And then we also proposed a simple topology, which has a limited control range, a detailed investigation of fault cases and the protection on the full-scale simulations and tested experimentally in the lab. And future work includes quantitative comparison of silicon and silicon-carbide devices for power flow controller in terms of losses and the thermal design, investigation of PFC with circuit breakers in the grid in the HVDC system, and then investigation of the coordination of HVDC grid protection and MMC internal protection. So this concludes my presentation. Thank you.
Thank you very much, Shubhangi. I would say we take a 10-minute break. So we a 5 to 10-minute break. So we should be back at Mats insists on 5 minutes, but let's try to be back at 11. And then we'll continue with questions from the opponent, Dimos.
Thank you. Yeah.
We were 15 minutes from this.
Okay.
टाइम ऐसे निकल रहा है क्या कर रही है Thank you so much. Thank you for showing up.
I will leave.
You are going to China or Denmark? Like permanently?
No, I will take part-time.
Okay.
We will meet. We will still meet, but not very often.
Yeah, if we can stay in touch in the email.
Yeah.
But thank you for showing up. It really means a lot. Oh yeah, thank you so much. That's perfect.
Yeah, thanks.
Welcome back after a short break. We can now continue with questions from the opponent, please.
Yeah, thank you very much. Congratulations for the nice work, and thanks for a very nice and well-structured presentation. I think you have worked in a very emerging and very interesting topic in your PhD, and I would say that I like the fact that this research spans from a component level, which is basically the new power module designs and possible modifications in the power module designs, up to the system level, and how you basically could apply this technology to mitigate faults or overcurrent operation. And yeah, I think I will take it topic by topic in my discussion here. And first, I would like to discuss with you the characterization of silicon carbide, because this is how you start your thesis, and I guess this is how you also start your research, by characterizing the overcurrent capability of silicon carbide MOSFETs, right? And please allow me some time to browse through my notes. Yeah, so that is basically chapter 2, and the publication is publication 10 and publication 7, where you basically took several samples of TO247 MOSFETs, right?
Yeah.
And you build a test circuit and start pulsing the components.
Yes.
I'm not sure if you have the possibility to draw.
Yeah, I can draw. I have paper and the board as well here if needed.
Yeah, whatever is most convenient for you.
And I have some slides as well if they need some explanation. I can do anything. It's okay.
Yeah, you can also project your thesis if possible.
Yeah. You said publication 7 and so that I have the right publication.
Publication 7 and I guess publication 10,
10.
where you present this characterization of short circuit capability.
Yep.
Great. And can you explain a little bit how you perform the tests and what kind of measurements, and how did you measure the different quantities? Because you present in your graphs the short circuit current, that's basically the drain current, and the drain source voltage and the gate source voltage. And you saw the different graphs there, different measurements for different values of the overcurrent or overload current. And you also estimated the junction temperature. So I'm very interested in discussing with you the junction temperature estimation and the way you measure the
all the quantities.
Yeah, exactly.
Okay.
And we will come back to the, sorry, and we will come back to this discussion also for the RDS zone later on for the gate driver design.
Yeah, so basically during, when we were developing the circuit, I used this capacitor, inductor, and a diode to make it a unidirectional sinusoidal pulse. And we used a gate driver in which there was, so when I was driving the overcurrent pulses until four times of overcurrent, there was no issue with the gate driver. I'm just mentioning first the problems we faced. And then secondly, when we increased the overcurrent, it was 4.5, I guess. And then suddenly the gate driver stopped working because of the desaturation. So we had to deactivate that desaturation thing so that we can perform the experiment until 5 times overcurrent. And for measuring the gate, for measuring this IDS on, so basically the current voltages, I use this Rogowski coil. I think it's called Rogowski coil. It's the one without any power supply. If you see the figure here in front of the capacitor. So we use the Rogowski coil to measure the current because it's not limited by how much current you can measure. And it was just perfect for the application because we could get very clean waveforms and it will not saturate basically. And then for the voltage measurement, we used these commonly used voltage probes. If you see here, I can tell the component number if you want. So we used those ones to measure the voltage, and then this Rogowski coil for measuring the current, and then I measured the gate signal directly from the function generator. That's how I measured them, and then these were the graphs basically. Figure 6 in the publication, or do you have?
Yeah, I'm looking on the thesis.
Yeah, sure. Or I can just show here. So.
Can we share for the audience what you're talking about?
Oh, sure. Here, or I can
Screen, yes.
I can put the same figure here actually, so that they know what I try to keep everything in the presentation. That's it. Here. So I was talking so far here. So this is the Rogowski coil voltage, a voltage measurement device here, and this is also the same. Yeah, so that's how I measured, and this was the curve for the failure when the devices failed at the first go. And then I have the similar curves for the cases when it doesn't fail actually. So if you would like to have a glimpse of that. Here. So in this slide, you can see on the right-hand side, these are the pulses, these are the responses for 2 times overcurrent, 3 times until 4.5, basically when it didn't fail. And then these are on-state characteristics of the devices before and after the tests. We can see there is a slight deviation in the 4.5 times of overcurrent. That's what I mentioned in the slide as well, that there was a difference of 3.5 and 4.2% in the threshold voltage. However, I didn't really notice much in the RDS on. So this was about the measurements. And secondly, I estimated the junction temperature using this formula, Tj is equals to Tk plus P average into Z junction temperature. I think I can just say
that's my follow-up question. So how did you reconstruct the thermal network of the device?
I actually did, so I did it as follows, because this pulse was for 1 millisecond. So even though if we add a heat sink or not, the characteristic will not change because it is such a small duration. It's 1 millisecond, and it takes around maybe 1 second to actually come the heat sink into the picture. So how I did is I took the T case temperature, which was ambient, plus the ZTH from the data sheet until the case. So here we can see this is the junction to case thermal resistance, which is available in the data sheet for different pulse weights. So I took that one for 1 millisecond pulse weight, and then I calculated the average, oops, this is the wrong slide show. And then I calculated the average power for, let's say, 5 devices for one particular overcurrent, and then that's how I estimated it. T junction is equals to T case plus P average into the thermal resistance between the ambient until the junction. So that's how I estimated the junction temperatures.
Okay, and what is the percentage error that you could consider for such a process of estimating junction temperature?
For estimation of the junction...
Because this is still an estimation. This is not the actual temperature measurement that you could do with a sensor, for example. Not in this specific case, but in a power module.
I mean, as we know, there are hotspots, and this number somehow gives an estimation, as you said, that this would be roughly the average. However, there could be a hotspot which has temperature much above than 250, or the one mentioned in the table as well. So on the corners, maybe it's, for example, for 2 times overcurrent, here or let's say 3 times overcurrents, I estimated 107 degrees centigrade in the paper. You can see here.
Yeah, I have the table.
Oh, you
That's
have it,
fine,
okay.
yes.
Yeah, 107, but at the hotspot, it could be much more than that. How much?
So what is the hotspot? Where do you expect the hotspot?
On the top of the
On the top of the die.
Yes.
Okay.
So it's an estimation actually, but the distribution would be as like hotspot, and then the temperature would decrease as we move further away. But it is just an indication in what range the temperature would be around that area and in the chip in general. So that's how I estimate it.
But for this very high current, that is 2 times or even 4 times the rated current, do you expect the estimation to be, as you said, that the temperature will drop as you move away from the hotspot? Or do you mean the hotspot of the die, or as you move away from the die, or as you move away to the package?
I was first mentioning about the die.
Okay.
So there would be hotspot on the die. And for the package, since it was a 247, so it's mainly the chip most of the encapsulation. So for 5 times.
So 5 times you already got the device broken, right?
Yeah. So I think the probable
current.
Yeah, the probable reasons for gate and source shorting was probably the melting of bond wires. So at the places where we have bond wires, the chip temperature definitely increased to maybe 600 or so, because that is the range where these bond wires fail when they are aluminum bond wire, which are the most commonly used one. So in terms of temperature distribution, how much variation would be there from? Is that what you were asking? Like how?
Yeah, because the current's very high, so I'm not sure if the temperature will drop, and the die is a very tiny piece of material, right? True. It's a few millimeters square, not even a centimeter square.
Yeah.
So the temperature might not be dropping as you move away. Or my other part of the question is, you have a die that contains several channel or several channels in parallel, right? It's not a unique device itself.
Yeah, that's true. I missed that.
So you might have a lot of hotspots, or at the end, you might not, macroscopically, you might not see any drop.
That's true. Yeah, that's true. You're right in that. Maybe the temperature variation is not that much because the heat is so much generated by this. Yeah, that explanation probably is true for normal cases.
Yeah.
But for high, I saw a paper from the previous student in which they were, during the short circuit, they had a hot spot, but it was not for 5 times. It was for much lower than that one.
Okay.
Yeah.
Okay, let's move a little bit further now. So we talk about the characterization. That's fine. You have done it for many different currents here and different conditions, and you estimate the junction temperature. And for 5 times the overcurrent, you basically got the device failed, right?
Yeah.
So what kind of failure mechanisms did you observe there?
Since these gate and short terminals were shorted, we actually wrote it down. We wrote it down. Probably there are 3 reasons. First is that this hot spot near to the gate oxide, and that led to the breakdown of gate oxide. And second one, as I mentioned, is the metal fusion of the metallization, and also maybe the melting of the bond wire. And so the third is melting of bond wires. So these are the 3 probable reasons we discussed.
Okay, but that's your hypothesis for the 5 times the current, right? Okay,
Yes.
Let's forget about this. Let's go a little bit towards 3 or 4 times that the overcurrent that the device have survived.
Yeah,
or all the devices have survived,
yeah.
basically, at 3 times and 4 times the overcurrent here and here. So there, and you characterize the device again in terms of on-state resistance and threshold voltage. My question there, or the point I would like to discuss with you, is why don't you check the breakdown voltage, the drain source breakdown voltage? Would this be relevant or not? Just out of curiosity.
You mean to say the breakdown voltage in forward?
The blocking voltage, yes. No, yeah, the forward.
The
yeah.
forward or the backward?
I mean the blocking voltage of the MOSFET, the drain source blocking voltage when the device is kept in the off state.
Yeah, yeah.
Has this been changed by applying several cycles of the overcurrent? Have you investigated this, or why you didn't do that?
Yeah, I didn't do that, but I can try to guess. Just a guess, of course. I didn't read about this one. So since RDS on VTH, at least the VTH changes when it is stressed for 5 times, so or 4.5 times in this case. So my expectation would be that, yeah, the breakdown voltage should change as well. How much? I can't say that for sure, but it should change.
Because it might create a lot of, or might excite a lot of energy in the drift region, and this might eventually bring the device close to avalanche.
Yeah, yeah, yeah.
Or not. But this happens when the energy is high or the voltage is high also. And in this case, you don't have a high voltage
no,
in
the
your tests, right?
voltages were not high. It's maximum of 58, and these were rated for 1200 volts. So, so the voltage may not be that high, but for the breakdown, I can't say for sure how it will look like. Since we didn't measure.
But how did you measure the other two parameters, namely on-state resistance and threshold voltage? Did you use a power device analyzer?
We used the curve tracer and took the characteristics and did the estimation from those curves.
Okay.
Yeah. But that's an interesting aspect about the breakdown. It somehow didn't come to my mind at the time when we did.
Yeah, maybe it's not so relevant for this case, but you should keep in mind that this is also an important parameter that you know dictates how the device.
Yeah, absolutely.
Or how healthy the device.
Yeah. For reliability, I think it would be an interesting aspect.
Yes. And then just a follow-up point to discuss here is why have you chosen to use a discrete component, a single die component for your tests and not a power module? Because later on in the later part of your work with the PFC, the power flow controllers and all the converters, we talk about high power applications, right? Several megawatt of power. So why did you choose a discrete component for your tests and not a power module? I know this might also be a practical limitation there, but okay.
Yeah, so the thing is, we wanted to do these tests, and we got in touch with the person from onsemi, and they were happy to provide so many devices. Let's say I tested 20 devices for one type of overcurrent, and I kept completely 5 different sets. So one was this practical limitation, as you mentioned, that these devices were very easily available. So this was the reason mainly to choose these devices. And then since they were rated for 30 amps and then until 150 amps, and we had the right components in the lab as well to measure for such devices until 5 times in this case.
So do you, or have you thought about what kind of observations would be, or what kind of changes you would expect if you, instead of a TO247 device, you test a power module, as you consider later on in this test, I mean, in the overcurrent characterization?
Yeah, my estimated guess would be, or from the work I did, so as we know that the heat sinks and other components of the power modules come into the picture in few seconds because they are further away from the chip. So if you test the power module for the exact same pulse, and since except the chip, no other components will be in, let's say, into this heat flow path or into the action in terms of thermal. So I would expect the similar performance. It could be the case that they fail maybe for 6 times overcurrent, but I would expect the similar performance in that sense because it's the chip which is playing the role for 1 millisecond pulse.
But what about the surrounding materials? Because you might have a little bit different material composition in a power module and in a discrete component, like a TO247 in this case. Would you expect some heat? I mean, the main part of the heat will be dissipated through the drain side that is cindered or soldered on the
Ceramic.
substrate, right? Do you expect some heat going or dissipated from the source side on the top?
Yeah, I think so. There would be some heat, and so the exact performance should depend upon the material inside the power module. For example, this silicon gel. And if I remember, I'm not sure the exact number, but the thermal conductivity is not that high. So not sure how much it will let the heat generated in the chip pass through it. So probably it will look similar, but it depends on the thermal conductivity of the material inside it.
It's, I guess, much lower compared to a pure copper or
Yes,
substrate or a
exactly.
DVC, for example, if you have a DVC substrate on the bottom of a power module.
So if it's low, if it's that bad, then I would expect it should be similar because there is no cooling way applied for 1 millisecond pulse in this case.
Yeah. Good. Okay, let's move a little bit further. I have a kind of comment here because I started reading your introduction chapter, and which is very nicely written, and suddenly I read about the silicon carbide parameters and their comparison over silicon counterparts. And there you mentioned that silicon carbide exhibits lower losses, higher temperature, can operate at higher frequencies and so on, and maximum blocking voltages. But what I missed there is the thermal conductivity also. That
it's 4 times.
Yeah, it's almost 3.5 or 4 times higher.
That's true.
And this is a key parameter for your investigation here, right? Because it's all about the thermal conductivity of the materials. And you talk a lot about this later on in the copper blocks and diamond blocks, whatever you investigate later.
Yeah, absolutely. Yeah, it was something which I should have mentioned since it differs by 4 times roughly.
Yeah. I think maybe one last comment or thing to discuss here is about the something that is not so clear, and perhaps it's nice to also set some constraints or an example there about the overcurrent or applications that require overcurrent capability. And you mentioned a few in your presentation earlier today. But can you really set some limits in terms of overcurrent time, duration, and peak current values for the application here? Because now here we focus on a PFC application in a MEST HVDC grid. And this is something that it's nice to set it and based on this design the overcurrent protection. I mean, both the passive one with the blocks and the active one with the gate driver, as well as the topology design for the PFC and dimensioning of the topology and components.
So if I understood correctly, you're talking about how much overcurrent we need for different applications.
Yeah, because you have included a table in your thesis about different from literature. That's,
it's in this paper, literature one, the paper one.
Yes. I think it's...
it should be at the end if you printed the same thesis.
Yeah, print the one you sent. It's on page 10 of your thesis. I mean, that the table 2.1.
Yeah, so it is the same which I was showing here. So this is the overload or overcurrent. In the literature, they use the term overload and overcurrent interchangeably, the difference being only that overload is generally considered for longer duration and overcurrents are mostly short circuit, ground faults, and so on. And these are the different systems where they actually said how much overload they need in different references. It could be a continuous one, and then we see, for example, in the last column of the same table, we see that the continuous overload is there for, how do I read this? So this is the overload 7 hour, 10%. Yeah, so for example, if you see the second last column with 7 hour and the percentage overload is 10, so this overloading will depend on how much time we want to withstand. If it's, let's say, 10, 15%, we can withstand for a few minutes or even hours as discussed here. If it's, let's say, 5 times overcurrent or 4 times overcurrent, which I investigated, then it definitely cannot be in hours or in a lot of minutes. So that was the aim that I was trying to put it down across different references, that it can vary from 10 milliseconds in the first column to hours in the last column, and even continuous, exactly in the last column here, through continuous overload of 10 to 20%. And this overloading will just depend on how long you want that. So that was the takeaway of this, basically.
Okay, yeah, this is fine, and thanks for clarifying. Now let's focus only on the 3 first columns, or number 2, 3, and 4, right? And those are references 46, 47, 48. And all these references focus on MMC converter, which is one of the most emerging topologies for meshed grids, right?
Right, yes.
Good. And here what I see is that the duration of the maximum duration of the overcurrent or overload, as you wrote here, operation varies a lot. I mean, a few orders of magnitude, from 10 milliseconds to 1.5 second.
Yes.
Okay, the overcurrent percentage is more or less the same. You never reach twice the load current. It's more like 20, 30%.
Okay.
So can you please explain why we have these differences?
Yeah, so I can try to...
Because this might also impact the way you design your module later on, right? Or the overcurrent, the cooling for the overcurrent.
That's true.
Mode of the module.
Yeah, so basically this overload duration, or let's say what is expected amount of extra power or the current you need, will depend on those this concept such as frequency reserve and those kind of responses. So I think they will be driven from that. That's what I tried to explain. So,
or I guess it might also be related to fault right-through operation of some converters.
Yes, that's true as well. So
stability of the grid.
For example, the ones I wrote down here they are due to primary frequency reserve, PFR, or fault clearance time, which I took a reference from one of our previous colleagues. And the time to clear the fault can vary from few milliseconds to 200 milliseconds, or even sometimes 600 milliseconds. So these overcurrent durations would be related to either this fault, as you mentioned, and also depending on primary frequency reserve, and related to those concepts, basically. I think.
Yeah, and I guess also depends on what kind of breaker you employ in your circuit, right? In the meshed grid, in the meshed HVDC grid or multi-terminal grid.
Yeah.
That's one thing, and the other thing could be the amount of semiconductor that one could invest in such a, one of these topologies.
That's true.
The cost. Exactly. And then this implies a higher cost, obviously, right?
Yeah.
Which is, as you mentioned in your thesis, that's one straightforward way to, or approach to increase the overcurrent capability, to parallel connect several components, either basically modules in this case. But can you see any challenge by parallel connecting several? I mean, parallel connecting 2 might be an easy case. You can have a good control of the operation, but what happens, or what do you expect if you parallel connect several? Because now we are talking about kiloamp withstand capabilities.
So while paralleling, there might be, while making the parallel connection, there might be a few parameters, for example, how their switching and conducting characteristics look like when they are switching. What they should be basically have similar RDS1 characteristics, otherwise there would be non-uniform distribution of the current among these chips. And another thing which I also mentioned in the paper as well is that we might have, it's in the paper, maybe not in the thesis, which is done for 312 kVA in the previous work of my colleagues, where they did a massive parallel connection, and they actually laid the circuit in such a way that these that this gate supply is uniformly distributed rather than being at one location, which decreases the size of loop, and hence the parasitics are also decreased. So this was one thing. And another thing is, as I said, switching characteristics should be as close as possible. And for that, I saw in some literatures, they may need some additional components to make sure that this happens. And also it depends on how the di by dt, dv by dt across these devices. So it depends on the switching characteristics in short from my perspective.
And I guess this is what you just mentioned about the switching characteristics is most relevant for high frequency applications like a power supply or a high frequency converter or high switching frequency converter. Because now, if we just go back again to the MMC case, as you might know, in MMC, you might not expect very high switching frequencies.
That's true, yeah.
So parallel connecting might not necessarily be the worst thing ever.
Yeah, it may not be. Yeah, it's not. I mean, I think paralleling the devices may not be a bad idea at all, because except the cost, of course, the cost increases drastically.
And complexity.
And the complexity and the connections and the control. But then if we have a lot of devices in parallel, we can have high efficiency, because there would be low losses per chip. So that is, I think, the design aspect one can think in that sense in parallel connections.
Yes. Good. Yeah. Now let's move a little bit further to the core of your thesis and your research. And that's basically the passive cooling approaches to increase the overcurrent capability. So first you test or you model and simulate several of these approaches.
Yeah.
And you start first with a copper block and copper block with phase change materials. My main question there when it comes to this, okay, you did a lot of modeling in FEM and simulations. Have you tried to manufacture and to build these modules?
I didn't end up in publishing that, but I did try a few things in the lab. For example, I was trying to measure the temperature of a very small tip. It was, I don't remember if it was 1 mm or 2 mm. But then I was trying to connect thermocouple on the top of the chip. But then as soon as I did, it was leading to the breakdown. So we tried a few things, but during the time when I was working on the overcurrent, I was mostly working on the simulation. So I did some few hidden trials, but didn't end up in the publishing so far.
Okay, so you tried to solder or cinder a die on a copper block? This is what you mean, or
I can show the picture.
Yeah.
So as I said, I didn't really publish about that because we didn't get that much result in general. So for example, this one here, it was just a few things I tried in the lab. These were the things available in the lab. And here on the left one, it's just one diode chip, which I had. I wanted to measure the voltage and current. Then the other one is, there is a very small block, you see, there is a here. Yeah, and then the structure basically looks like this. I was trying to clamp it, and as I said, I was trying to connect this thermocouple on this one, and then I tried with this one. This device basically broke because I was trying to make good connection, and in that this and the surface of the tip of the thermocouple was not meant for the use and to be soldered on that one. So I did try that. However, I didn't publish the results so far. And then I changed the topic to, I mean, not change, I continued with the project of power flow controllers in that sense.
Yeah, I see, that's okay. But okay, now I go a little bit further with my question now. But in this case, you have a diode, as you said, a diode die, right? That is anode and cathode. And the top and bottom is anode cathode or vice versa. Which might make it a little bit simpler if you want to design or implement or manufacture this double side cooling or single side cooling, whatever you target for. How or what kind of challenges do you foresee when you have an active device?
Like MOSFET.
like a MOSFET, for example, where the gate pad is super tiny, and you can barely fit one bond wire. If you try to build bond wires on this, it's even challenging to build one bond wire.
Yeah. So actually, this top cooling has been investigated in some of the power modules by industry here. So, for example, one of the commercial one available I saw in the news recently is this one. Here, they have clearly given these pads for gate on the right side, and the other side is just which you can center probably on ceramic or with copper clips or anything which has higher current capability than bond wires. And the similar things were done for example, this one here. This is a slide which I took from the report. Here, for example, in this one, they have used copper clips and very small number of bond wires for the gate because we don't need very high number of bond wires. Similarly here, these are the copper blocks, and this was an interdigitated structure on the top for gate and source. So they used specifically for so here they have actually implemented by using, and so if it's a die and they just not put the top cooling thing on the gate, but the rest of it. And if there is an interdigitated structure like grooves for the gate and source, you can just put a copper block on the top, and the grooves will have the gate thing. So they will not be touching each other. For instance, here in this one, this picture here, you can see that there is a wire for gate, and then you can just have a copper block or increased metallization on the top of the chip, which would be very similar to the one for which I did the simulations for.
Yes, and now coming to the block,
Yeah.
to the copper block,
Yeah.
And the copper block with the phase change material. Can you please explain why you choose this specific geometry for the copper block with phase change material? I mean, why just having four cylindrical channels and not a common kind of rectangular, or what are the constraints? Why did you choose this shape?
So I was actually in touch with a research group from University of Warwick, and they have done the measurements for the copper block with these four holes for phase change material. And they were able to do the experiments for the same. And also they had this experimentally verified COMSOL model, which I got from them. And that was the reason I used the exact same geometry, because I have the full details of the power model inside, which is which is very difficult sometimes to get through the manufacturers. So they had this model for this particular power module. So they had the model for this phase change power module, and in that one I kept everything same, except that I removed these holes and kept a block basically, so that I have more confidence that whatever I'm doing will make sense, because this model has been tested experimentally by other researchers. So this was the reason for this geometry and all the parameters you will see in the paper.
Yeah. Okay, and a follow-up question here, because in your thesis, several places you talk about 1 square centimeter of die area, which I guess is not devices that are available today in silicon-carbide. So usually the silicon-carbide devices are much smaller, right?
Yes.
The ones at least you can get commercially, or you can get as samples. How or what kind of challenges, or how easy is to implement these small copper blocks for each die? Because that's something, that might pose limitations when you manufacture.
Indeed,
this kind of approach. I mean, the approach is fine like that. My main concern, or what I would like to discuss with you, is how you could make it so small and place it on top or on bottom of the die. Okay, bottom might be a little bit easier
comparatively. Yeah. So if we really need overcurrent capability for a device, then it will definitely be an extra step that we definitely cannot avoid. But as you said, it will be much easier on the bottom rather than top because we have bond wires on the top. And then if you want to put it on the top, we will need a different analysis altogether. But for the bottom, it will be, I shouldn't say just an extra step, but it is still easier than doing the modification on the top because it will involve just one additional step of adding or centering a copper block, basically. Centering, I'm saying, so that it's more reliable, has high thermal conductivity. So yeah, it will be an extra step, but that would mean more cost of the material, more size of the power module. But if there is an application where you do need it, probably either you can parallel or use these kind of power modules. Yeah.
Yes.
Yeah, but it's an extra step. I completely agree with you on that.
Yeah, it's an extra step on the manufacturing process of the power module.
Yeah.
Because I have the same question when it comes to the copper block with microchannel cooling. I mean, again, the microchannel, it's a very nice concept that might be already used in double-side cooling. But when it comes to this one, that you have to put it on top of its die, I mean, the same challenge anyway in what exists, but how easy is to manufacture the small, the tiny microchannels with a very tiny cross-section?
Yeah, I mean, as you said, it will be, it's not, I'm not sure if the I'm not sure if these microchannels are commercially available as of now for power modules. But then there is a research group in EPFL who have built a converter, and they have implemented microchannel channels at 3 levels. I can show a picture, and it's there in the paper too. So they have built the microchannels from the system level, which is heat sink, to the device, just below the device. And then they also made some experiments with microchannel inside the chip itself, below the die, basically. So of course, it will be challenging, but then if the gain is so much in terms of overcurrent, as we have seen, it's the highest duration with microchannel cooling, then maybe it is worth spending that money. But yeah, it will require a lot of manufacturing technicalities and complexity for sure.
Yes.
And also one needs to take care of the liquid flowing through it. It has to be insulator. For example, the one I mentioned, deionized water. So basically it doesn't have ions or it doesn't conduct electricity. So it will need a lot of things to consider, for example, the material, the cost, and liquid and its cost at the same time. And the maintenance goes on for an active system as well.
Yeah, I will come back to microchannel cooling a little bit later and have a couple of questions. But I have another question now when it comes to your results on page 23 and 25. It's figures 3.2 and 3.4.
It's in the thesis, right?
In the thesis, yes. So I guess those are publication 3 or...
Yeah, so 3.3 you said, and 3.2.
3.2.
Okay.
Can you please elaborate a bit on the results here?
Sure.
Because those are concerned to different applications, like the inverter, the drive application, motor drive, and the DC-DC converter application.
Yeah, I will put the slide here so that everyone else can also see. So we are talking about this one here.
Okay.
It's just the similar diagrams, but for silicon carbide. So in figure 3.2,
yes.
In figure 3.2, on the left, it shows the response of the standard power modules and the one with copper and copper plus PCM for the silicon carbide for inverter application, and on the right side, the same for silicon carbide. But then the thing here is that the response depends on the heat flux at the end, whether it's an inverter drive or it's a DC-DC converter. And yeah, so I investigated these two cases because these are among the most commonly found applications. So that's the reason we did the investigation for 2. And in the 3.2, this is the response, but we can see that on the left side for the silicon for 2 times overcurrent, the temperature, during the steady state, the temperature is around 50 to 55-ish for all the power modules. But then the temperature may not reach its thermal limit. So technically, there is no need for 2 times of overcurrent for any modification in the power module. This is one takeaway. And for 3 times, maybe because the melting point of the phase change material in this case is around 108 degrees centigrade. And similarly, for 4 times overcurrent, you may actually need it, but there's not a huge improvement for the silicon power module. On the other hand, there is some improvement on the silicon carbide cases because the overcurrent durations are shorter as compared to the silicon cases. Similarly, for 3.3 diagram, this phase change material, for example, let's talk about 3.3, figure A. In this one, for 2 times overcurrent, the temperature doesn't reach the melting point of phase change. And hence, there is a straight red line for the melting of phase change material. Similarly, for 3 times, there is an increment, but the phase change didn't melt completely because it was not that high power flux, probably. And then for 4 times overcurrent, the power was high, the duration was enough, so there was enough time for PCM to melt. Similar explanations can be given for the figure 3.3 in B. For 2 times overcurrent, all the phase change material melts, and because the duration was somewhere around few seconds, it was 7 or 8 seconds in this case. So phase change material has enough time to melt. For the 3 times overcurrent, it melted, but not completely because the durations, as you can see in 3.2D, is less than 1 second. And for 4 OC, it's a straight line. Similarly, depending on how long the overcurrent duration is, the same explanations can be given for the melting of phase change material, depending on how much power we had and how much duration we have. So in this one, what we found out was that, as you can see in the figures, there is not much increment in the overcurrent duration, even though you have phase change material, mainly because of their comparatively lower thermal conductivity. For example, lithium, I considered for silicon carbide, that had thermal conductivity of 85 when it's solid, and it increased, I assumed 4 times because of the convection when it's melting. Even though I assumed it 4 times, it still is not better than just a copper block. So it comes down to the thermal conductivity of the material you're putting on the top or bottom, whichever module you design. Yeah.
Because here you have 2 different applications, right? And the observations or the results for silicon carbide, they look more or less the same.
Yes.
In the motor drive and DC-DC converter application. But when it comes to silicon, you might observe some differences.
Yeah.
So my concern or my question is, do you see any application-specific reason for these 2 different observations here? Because I guess the operating parameters of a motor drive inverter and the DC-DC converter vary a bit or differ a bit.
Yes, so it depends. So the characteristics you're seeing different for silicon for 2 applications is because of following reasons. First is that the power or the losses in the inverter drive are lower than the one for DC-DC converter, because the RMS and the reason for that is that the RMS value of the current should be high, or the losses are higher for DC-DC converter. This is one reason. That's why you see that in figure 3.4B and C, it actually reaches its thermal limits of 175 degrees centigrade, which I assumed. And the other reason is also that for the difference in the characteristics is that I shortened the module to half, and so the area available for the bigger chip in this case for per unit area of die hypothetically is larger than the one available for inverter. So that was also the reason that there is a slight difference in the steady state temperature before the overcurrent occurs. So this is for the steady state, and for the transients, I would like to say that the power per unit area is different, and combining these two parameters, that power per unit area and the available cooling circuit available per unit area of the chips are different for these two applications. So this is the reason, in my opinion. These are the two reasons, in my opinion, for this difference in the behavior.
Yeah, so you could basically adjust the parameters or the design and make the two cases, the two application studies such that the IGBT or silicon carbide temperature, steady state temperature, are the same for the two applications. Because now the steady state starts from 50, or as you said, 55 degrees Celsius for the inverter application. For the DC-DC starts from 80.
Yeah, so yeah, I mean, if you can increase the cooling, then you can actually compare on the basis that we have higher cooling for DC-DC application, or let's say for the heat sink, then we may be able to tune it in a way that for this application as well, it is exactly the way it was for inverter. But for the fair comparison, I just kept the same, the power module, so that we have the exact same thermal circuit for both the application, and yeah, enhance the difference in the two cases.
Yes, and yeah. And talking about adjustments and choice of materials and stuff, can you please explain a bit why you choose this amount of phase change material? Now I'm trying to find it. I think you mentioned in your thesis that you use
it's 38%.
30 or 38%. Yes.
Yeah, so the thing is, there is a trade-off when it comes to the phase change material application because of their lower thermal conductivity. So first we want to have first criteria is that we want to have phase change material as much as possible, because this will give us more amount of heat to be absorbed in the form of latent heat of this phase change material. So from that perspective, we want it to be as high as possible. But as I mentioned, they have much lesser thermal conductivity. So you will have a very delayed response time if you have a lot of phase change material, let's say. So there has to be an optimum selection so that we can use the thermal conductivity of the metallic structure containing phase change, and at the same time we can use the latent heat of the structure. And this optimum was found out from the investigation. I didn't do the investigation for that. The research group from Warwick, which I mentioned earlier, they did this investigation for different phase change percentages, and they found out it's best to have somewhere between 30 to 50, 60% in order to tune both the heat absorption as well as the thermal conductivity. So this was the reason, and I kept the same because they tested the same thing for 38% experimentally. So I kept exactly the same percentage.
So you didn't run any optimization in this?
No, I didn't run the optimization.
Find the optimal percentage. Okay.
No, because they already did it, and they somehow came to this number. So I trusted them for that matter, and they also did the analytical and COMSOL simulations to give a range. But the most optimum was, if I remember correctly, was 50%. So that we give equal weightage to the latent heat as well as the response time of this arrangement.
Yes, thank you. Yes, and then you also try the top and bottom cooling.
Yes.
Where you include two copper blocks, one beneath and one above the die. And you did more or less the same investigation using COMSOL models and FEM simulations. My question there, apart from the results and the observations here, is what this double-side cooling implies for the parasitics in the circuit. You mentioned something in the paper. I think that was. I need to check quickly.
Sure.
Yes, that's publication 3.
Yeah.
Where you discuss the double side cooling.
Yeah.
Or you discuss all of them, but let's focus on the double side cooling.
Sure.
And there you, or even, sorry, it's also another publication that you discuss this.
Mm-hmm.
I think publication number 2.
Okay. Yeah.
Yes. Yeah, it's publication number 2, sorry.
Okay. Yeah.
Yeah, where you discuss the copper block
Mm-hmm.
and basically what we already discussed for in the thesis. Have you tried to extract the parasitics of the new module design using your console simulation model?
So the main focus of this investigation that we were actually trying to investigate was to mainly look at the thermal dynamics or the thermal response of power module. So we didn't specifically look for inductive or capacitive parasitics in that matter. But in my opinion, if we are able to manufacture this power module, we should be able to mitigate them by a proper circuit design. Maybe it could be a distributed power circuit or distributed gate voltages for them. But in that particular case, I did not really investigate the parasitics from the console. It was mostly the thermal investigation which I did, and the comparison of copper and copper plus phase change materials.
What do you think? I mean, you have a double side cooling, like a copper block on beneath
Bottom
the
and top, yeah.
yes, bottom and top, and you eliminate the bond wires. So that's fine, right? So we eliminate the bond wires thermally. The entire structure might be more stable and under overcurrent operation, as you explored. But then you add 2 blocks.
Yes.
One beneath, one below. And let's say we accept that the block beneath might contribute to higher temperature at steady state and during normal operation. How these two contribute to the parasitic inductance and how this compares to the parasitic inductance of bond wires. Because you gain something, but at the end, you replace the bond wires with the 2 copper blocks, which is a nice concept.
You mean the bond wires on the copper blocks, or?
Yes.
Okay.
Or, if I understood well, you replace the bond wires in the double side cooling, in the double or top bottom cooling with a copper block. And the copper block is what conducts current from the source side.
Yeah, in this one, yes, that's what I'm assuming, yeah.
Exactly.
Yeah.
Which means that the current flows through the copper block.
That's true, yeah.
And sees the parasitic or stray inductance of the copper block itself.
For that one, from my literature studies and the investigations studies which I read, I think it should have lower inductance as compared to the one with bond wires, because I was checking some power module designs from different industries, and they had a very similar concept. This is the one with bond wires, but I'm not sure if I have that slide. But then, for example, I was reading the literatures about these technologies. These are all planar technologies which don't have bond wires. And they mentioned that their inductance, this parasitic inductance, was much lower than the one with the bond wires for the exact same chip. So I would expect the same. Yeah, because maybe there are not many loops because of this, because we have these straight lead or connections or those copper blocks for. But if I compare these ones with the ones which are already proven by industry, I would expect lesser inductance in that case. But of course, we cannot add too much of material, otherwise we will end up being higher. For example, in these cases, they increased the thickness of metallization in some cases. So and that further was connected by copper clips or something. Even in the power module design, which I showed, we can do the same, that we kind of increase the thickness of metallization, which can further be connected to the external circuit either by copper clips or lead frames, and copper clips, lead frames, and there are a few more concepts I forgot, I think.
Ribbon.
Wedge bonding, for example. So they seem to have less inductance as compared to the conventional bond wires.
But I guess the inductance also depends on the geometry. Yeah. So as the height goes up,
it increases. It should increase, in my opinion.
I think it should decrease, in my opinion.
Okay.
Which means that if you increase the thickness or the height of the copper block,
yeah,
the inductance should go slightly lower.
Okay.
But on the other hand, you increase for a given cross section.
Yeah.
And then you increase the thermal resistance.
I mean, if it's on the top, yes, the thermal resistance of the whole block would increase, yes. Is that what you were?
Yeah. My main question is how this approach compares in terms of parasitic inductance with the bond wires.
I mean,
because I guess overcurrent operation will happen once every long time, but during normal operation of a converter, you always have to see this parasitic inductance, right?
That's true, yeah.
Which is the main operating mode of inverter or DC-DC converter, as you studied.
Yeah. I mean, I just assumed from these literatures available that if we keep it below a certain height, we may not see much of inductance. But if you say it increases, it decreases with height. I mean, from these, after reading these, where they increase the metallization width, basically, or use the copper lead frames to connect it to an external circuit, they saw reduced inductance. Since I didn't really calculate the inductance for that matter, yeah.
Because it would be quite straightforward to extract the geometry from the FEM simulation model and run it for the magnetics.
Okay. Yeah, should be fine.
Yeah, in Console,
it's about
for
the
example,
settings.
or in any other tool that you could consider.
Yeah, that's an interesting aspect, actually. I could have maybe measured it for a few, and that would have given a clear estimate of that, yeah.
Yeah, and then you could transfer these parameters to, for example, a SPICE simulation and investigate the impact of parasitics on the overvoltage, for example.
Yeah, that's a very good insight, actually, yeah.
Yeah, let's move then to the microchannel cooling. And that is the next chapter in your thesis. Yeah, my first point here to discuss is related to figure 5.1 on page 35, where you show the thermal resistance and the number of microchannels.
Yeah.
And it's quite obvious that as you increase a microchannel, number of microchannel to a certain number, the thermal resistance decreases.
Yeah.
So what kind of practical limitations could you see there? I mean, it's nice to increase the number of microchannels to something very high, and the thermal resistance goes down. How practical this approach could be?
So in terms of the flow rate, as you can see in figure 5.1b, the second figure on the right, so there is definitely a decrement or reduction in the thermal resistance. However, the rate of reduction in the thermal resistance is not that high as you proceed for higher flow rates. So the slope gets less steep, basically, as you proceed for higher flow rates. So that is one thing which can be considered in the design process, that what is really the flow rate we are looking for, because it will if we increase the flow rate, and the size of the pump would be increased as a result. But the thing is, will we get as much as we increase? Will we get as much decrement in the thermal resistance as compared to the amount of flow rate increased? So this could be one aspect, that the decrement in the thermal resistance may not be that high, or maybe not that worth as we increase the flow rate, because we will need a bigger pump basically to pump more liquid.
So in your modeling there, do you consider laminar or a turbulent flow?
It's a laminar flow.
So the Reynolds number is below 2000, let's say.
Okay.
Because that's something you mentioned in your, that's what I'm trying to search for here in one of the publications. I need to check it.
Yeah, let me see, where is it? Yeah, so I think you're talking about publication 9 here, I guess.
I guess so, yes.
Yeah.
Yes, publication 9.
Yeah. So here I have given these formula which I took from a reference, and when I was calculating, I just put down everything. I didn't really look at the individual values. I explained this so that the reader can understand how I came to those graphs and those numbers for the thermal resistance. But in my simulation, yes, I assumed laminar isothermal flow. Yeah.
Okay. But would you expect a better thermal performance using or considering a turbulent flow?
Well, if the flow is turbulent, then there would be more movement in the particles, and hence its entropy, or the temperature at microscopic level, is expected to be higher than the laminar. So probably worse, if I think it like that.
Okay.
And I'm not sure how the bubbles would look like inside. If there are bubbles, then it definitely reduces the cooling performance during turbulent flow.
I would say it's the opposite. At least I see it as the opposite, that with a turbulent, you push more power, or you pump, or you need more pumping power, and this, how to say, gets the power out more effectively. That's how I see it.
I
With a
mean,
turbulent flow.
if you're saying about pushing the liquid too fast, then it would mean increment in flow rate, basically. So which means the cooling would be higher from that perspective.
Yeah, but you might change from laminar to turbulent flow. Would you?
I mean, it should.
If you increase the flow rate for a given cross section of the microchannel.
Yeah, I mean, I set it one particular limit for one arrangement, but for the transition from laminar, I think it should be possible in COMSOL by defining the events, which I did the same thing for turning on the macrochannel. So probably it should be possible. I mean, and it may be worth exploring, as you said. Yeah.
And yeah, staying a little bit more on the macro channel, sorry, cooling. In your presentation, you mentioned that, if I understood it well, that you enable microchannel operation only during the overcurrent protection. So how do you envisage this? Is it something like a controller that should be implemented and control the operation of the pump? How do you see that?
Yeah, so theoretically, how we can see that generally for this operation to happen in real life, we will need a communication system which will give a signal to turn on and off the pump, basically. So it will basically rely on the communication coming from the system, how the current is going to look like very soon, or is it or is it already there? So yes, we will need a controller to turn on and off. Or the other thing could be that we've let the liquid flow through it at a very, very low rate, and so that it's on, and as soon as there is an overcurrent, we can just increase the flow rate to a very high value, and then there is an intense cooling involved. So in that sense, yes, we will need a controller to sense, and then that can give further the direction to the pump that, okay, turn it on, turn it off.
Yeah, that's more like an active cooling, right?
Yes, in that sense.
Approach. Okay, let's say that, okay, we go for that. You let the water flow continuously during steady state of operation, and then suddenly an overcurrent occurs. How fast are the dynamics, the response, the dynamics of the response of the cooling system with the microchannels?
Yeah, that's true. Yeah.
When it comes to the overcurrent, because overcurrent might happen within a few milliseconds.
Yeah.
Based on your investigation, and let's say that you have to enable the water to flow faster, so you increase the flow rate, basically. So how have you thought about this? How fast should this be, or is it feasible at all to do it like that, or you need something like a gate driver that we will discuss on?
Well, about communication, I think that should be quick within few milliseconds, but turning on micropump might be a limitation. Here I assumed it starts as soon as the overcurrent arrives. There is no delay. But in real life, if there is a delay, because it's a mechanical system, so the response time might be...
It's a thermodynamic system.
Exactly.
The response time is much slower,
Exactly.
or longer compared
That's
to an
true.
electrical or a semiconductor system.
Yeah, so in that sense, probably the limitation may not come from the communication, but it will rather come from the starting of the micropump. As you said, it's a thermodynamic system.
Yeah, I guess
so...
communication will happen within microsecond scale,
okay.
right? If you have
it's even faster than I thought. Okay.
If you have a fast sensing system, somewhat, and
yeah,
or I mean, the sensing signal to the microprocessor or the processor, digital processor, should happen quite fast compared to the dynamics.
Yeah, exactly. So I think the limitation, if it comes, would be from how soon we can turn on or change the flow rate. It won't really come from the communication. That's true. Yeah, if it's, let's say, 1 or 2 milliseconds in turning on the micropump, then maybe it won't matter. But if it's, let's say, 500 milliseconds or 1 second, then the dynamics will change quite a lot in this case. And it will just increase the temperature in that sense.
Yeah. Yes, let's move to the gate driver.
Yeah.
That's an interesting concept, which also belongs to the active thermal or overcurrent mitigation approaches.
Yeah.
That's chapter 6 in your thesis and paper 4, right? So again, we come back to the device characterization, because you have performed several characterizations here for the on-state resistance. And you also presented this in your thesis, in your presentation earlier, that you used 2 models, one with a 3-terminal, one with a 5-terminal, which contains the temperature.
And case.
Yeah, exactly. At case, and also junction that you can measure. And the third approach is experimentally, right?
Yeah.
Can you describe briefly how you measure the on-state resistance?
Yeah.
Because that's a key parameter for your driver, right? To choose or to tune the driver parameters.
We are talking about figure 6.1 in the thesis on page 40, because I don't have I'm just telling them, because they don't have the...
exactly that one. Yes, this circuit, the measurement circuit.
Yes.
Or the testing circuit.
Yes. So we have used a power supply to change the voltages basically for the gate source voltage, and another supply to change this, to let the current flow, 20 amps in this case. How I measured was that we were turning on and off and measuring and taking the measurements very quickly, so that because we didn't know at what gate voltage, the device will fail. So we were like, turn on, turn off, and took the reading continuously. It's me and Hansi did it together. So one was switching on and off the supply, another one was writing. So that's how we took the measurements at different gate voltages. Yeah.
And how long this turn-on pulse?
I mean, it should be a fraction of a second because we were like on, it was done manually without a controller. So we did turn on, turn off by hand as soon as we could so that we don't fail the device because of the increased gate voltage.
Okay, so it was basically a pulse test with a pulsed current.
Yes.
Right?
Yes.
But the duration of the current was, I would say, if it was 1 second, as you said, that was perhaps a little bit longer compared to what the curve tracer, for example, use as a pulse duration that could be tens of microseconds or a few hundreds of microseconds,
Yes.
right?
Yes.
So my question there is, did you consider the self-heating effect of the die when measuring this on-state resistance? Because you push current for a second or even shorter than a second, let's say, and then you create losses in the die, right? That eventually increase the junction temperature.
I mean, there would be increased junction temperature for sure with these pulses, but since it was so less, then I mean, we were taking some breaks in between the measurements so that the die cools down before we take the second measurement. For example, we tested at 20 volts and then we took few minutes, let the die cool, and then did the same for the same device. We did it for 25, let the die cool, and so on. And that's how we did it.
That's fine. But then for the 20 volt of gate voltage, 25 volt, 30, and so on, how did you make sure that the measurement is taken exactly at the same time instant as the other ones, like the 25 for with 30 and 35 and so on?
Are you mentioning about the pulse duration in that sense?
Yes.
So we
and the time point, the time instant that you measure.
So when we were measuring these ones, I took the first measurement I saw, and then it was decreasing as well. So we took the measurement which was first visible, and then I took the same method for the rest of the measurements too. So for example, as soon as we turn on, we saw what was the first value, and then we just noted down. So that's how we did it for all the ones. So I always made sure, it was a lot of manual work rather than automatic. So we always made sure that we took the first value we see, because as the device heats up, because of the continuous increased gate voltage, we may see a difference in the drain source voltage. So that's why we took the first value we saw, and that's how we tried to make it in the same fashion for other measurements too.
And how did you measure the on-state voltage and the current in this test circuit?
So the on-state current was the one which was supplied by power supply, so we knew it. And for the voltage, we used those voltage probes to measure the voltage and
the multimeter or high resolution multimeter.
Yeah, I think it was multimeter. Yeah.
Okay.
Yeah. Not the probe. Yeah, probe is for the waveforms. Yeah.
Okay. So have you thought about the difference or the reason behind the difference between the experimental results, the red plot on figure 6.2 and the black and gray plots or waveforms on this plot?
Yeah, I have some
Because
ideas.
you have an offset, sorry to interrupt you, there's an offset between the simulation results, even with the 5-terminal component that use or takes into account the temperature impact, and experimental results. And more or less this offset is, I would say, constant, especially for lower gate source value, voltage values.
Yeah. So more specifically, you would like to hear the comparison between experimental and the other two models, right?
Yes.
If I understood. Okay. So first, there might be few reasons, which I think could be the reasons are, first of all, the way we were measuring it was more manual. One factor could be that, of course. And second one, I used the same devices which we stressed for 2 times of overcurrent in the testing of devices which we discussed previously. So if you remember this LC circuit, I used for until 5 times overcurrent. So I just took one of the devices which we stressed for 2 times of
So
overcurrent.
you already took, you didn't use a healthy device, but a device that has already gone through a stressing process.
Yeah, it was that device. So that's why there might be a shift in the performance of the device. So this might be another reason, I think.
Because for the second plot, what was the conditions that, or what are the conditions for the red dot
Yeah.
that was taken from the dataset?
Yeah, so I took this value directly from the data sheet and it is for 20 volts as we can see, and in the data sheet they give this curve for so they if I remember it was calculated. Let me try to remember that. Close to.
Yeah, I guess this is the value that is given in a data sheet.
Yeah, it was definitely it was definitely taken from data sheet, but
under some measurement or experimental conditions
okay.
of certain gate voltage and drain current, right?
Yeah, so this data sheet, if we are talking about the pulse width, they use this 250 microsecond of pulse to measure basically these resistances, on-state resistances. So I definitely took this from data sheet, but I'm trying to remember if it was I calculated from V and I
from the
or
plot, or you took it from the table.
Yes, that's what I'm trying to remember, but I'm not able to recall. From my guess, I think I would have calculated from the plot of V and I.
Okay.
And the data sheet uses 250 microsecond of pulse. If I think this is what you were looking for.
Yeah, that was what I meant earlier. Yes.
Yeah.
Because what I would like to discuss is that the dataset value matches with simulation data, but the experimental plot is a little bit shifted. Yes, has an offset towards higher values.
That's true.
And could it be the temperature effect, the junction temperature effect, or is it some parasitic resistance that might be, measured when you, or in the way you connect the probes in your setup? Or both?
Yeah, it could be both actually, because as we can see in the figure, the cables were not the shortest cable I used. So it could be an impact of both. And yeah, I mean, from the data sheet, they are matching so well because I use the exact same pulse duration in the LT spice, and I could just control the pulse in the simulation. So I think this could be the reason what you said is this stressed out device and also this inductance in the circuit.
Okay.
Yeah.
Okay, let's accept that this is fine, and you use this to tune your gate driver, right? And you develop this gate driver, which I like it a lot. It's a very simple and still approach that could actively mitigate overcurrent.
Yeah,
I'm talking about the gate driver, right?
Yeah, yeah.
And the thing that I would like to discuss with you here is how the operation of this driver is done. I mean, okay, let's say that you detect an overcurrent operation or overcurrent condition, and this means that you use a DSAT circuit.
Yeah.
Here on the drain side, this sends the overcurrent, gives a signal to the logic circuit, and then you enable the turn on of the VOC supply.
Yeah.
My question there is how do you see the transition between the normal driving operation with, let's say, plus 20 volts to something that could be plus 35 volts, for example? So do you turn on VOC while having the V plus already on? Do you imagine a switching or a kind of transition between those two? Have you run some simulations on this?
So actually, this was just a proposal.
Okay.
We didn't do any simulations or experiments about this. It was just a proposal of idea that if we want to implement this gate augmentation method, it doesn't have to be very complicated. It can be as simple as measuring the on-state voltage and turning on and off this voltage supply for this application. And you mentioned about the transition of, let's say, plus 20 in this case to, let's say, plus 35.
Yes, because the gate will sit plus 20 during steady state, and then when overcurrent occurs, then it will see plus 35, for example. But what happens here? I mean, how you go from the plus 20 to plus 35 and vice versa, from plus 35 to plus 20 when the overcurrent has gone?
From this picture, so here it will be, let's say, this VOC would be applied across the gate driver. So the transition, in my opinion, would depend on the response of your driver circuit at the end, how you design it. So if the it would be very similar to, let's say, the turn on and turn off of the gate driver. If it's within few nanoseconds or microseconds, if it can turn on the supply, if it can do the transition from, let's say, -5 to +20 in few nanoseconds or microseconds, depending on the design, then it should look similar for that, because we can implement the same logic of turning, increasing the voltage to that. So it can be very similar time response regarding increment and decrement at the same time. Is that what you were looking for?
Yes, more or less, because in the circuit diagram that you present on figure 6.3, that's a very ideal one, right?
Yes.
So you don't include any parasitics, any stray parasitic inductance, for example, because there should be some parasitic inductance.
Sure.
If you implement this in hardware, in a printed circuit board, right?
That's true, yes.
So a few nanohenry here and there, even a few nano or a couple of nanohenry between the output of the integrated circuit of the driver and the other branch with overcurrent voltage. So do you see any problem there with having two voltages?
Well, since it was a proposal, so we didn't really build this one in the lab, but if we want to implement this, then I think, as you said, it will be important to see how the loops are for the connections, and we might have to do some optimization in terms of the distribution of the components across the driver. So yes, inductance, parasitic parameters may come in the picture, because there would be a loop, basically.
Okay. Yes.
Yeah.
And how would you implement this in reality? What kind of switches would you use for example, for the VOC? Or I guess the totem pole here is a kind of typical integrated circuit driver.
I mean, here we can either use something similar to the one available in conventional one, or I think it should be very similar to the conventional one, the kind of switches we use, so that they can do the transition very quickly. Otherwise, we may be late in terms of saving the device by the time. If we implement the switch I'm talking about is VOC, if we implement a slow switch, it may be too late for the device to be saved. So if I can, I would try to use the similar switches so that it's as fast as the gate driver.
But in terms of response, what is the bottleneck here? Is it this switch itself, or is it the response of the DSAT circuit that you would implement here, right, on the train side?
Yeah.
Because if you accept some more or some larger circuit complexity or operating complexity, you could use a sensor, a current sensor, by accepting perhaps some additional stray inductance in the circuit, and use a controller or digital controller to
sense.
yeah, to sense and control the
Mhm.
switching of these additional switches, which
Yeah.
increase the complexity. But everything depends on how critical this could be for the application itself. I mean, how
That's
critical is
true. Yeah.
to mitigate the overcurrent for a short period of time.
I mean, in ideal case, we would like to sense it as soon as possible. But when it comes to reality, there would definitely be some delay. It could be from maybe few microsecond to, I'm not sure if it's, we would not like to have it in the range of milliseconds for sure. But in an ideal case, we would like to have this sensor working as soon as possible. That's how we would aim to design it for, if we can.
Yeah, so it should be microsecond
I think
scale
so.
or even,
Yes.
yeah, few microseconds.
Yes.
Great, thank you. And now it's time, I think, to move to the power flow controller
Yeah.
design. Here in this chapter in your papers, you investigated performed evaluation of different topologies in terms of component and sizing, I guess.
Yeah.
Right?
Yeah.
And what I would like you to explain a bit is about the choice of components, because by reading the thesis and the paper as well, I see in different places that you talk about number of components, number of capacitors, number of switches.
Sure.
And then later you clarify a little bit more and say that the switches are compared in terms of ratings, right?
Yeah.
Volt ampere
Voltage
rating.
blocking.
Yeah, voltage
yes.
blocking, or could be also volt ampere rating, which is basic, or chip size or whatever losses, normalized losses and so on. What I missed a bit is how you quantify the capacitor metric to compare the different topologies.
So if we see the figure 7.6 on the right side of the thesis, so here I'm comparing the capacitor, the topology with one capacitor and topology with two capacitors. In the first one, we can see that, so the limit of the current passing through the capacitor is, the limits are 300 amps and 1200 amps, and this is changing the direction. And on the right side, it is, the currents are flowing through the capacitor. It's the same capacitor, it is the same current, which is flowing across these two. So here the sizing of the capacitor can be done according to the RMS value, which it can withstand because of its thermal limitations. So that's how we can try to design the capacitor in terms of how much RMS it can withstand. And for the two capacitor topology, of course, we need two capacitor, and hence maybe the prices are higher for, I mean, the combined prices of these two capacitors is higher than the single capacitor rated for the same current. But we have to keep in mind that, as shown in figure 7.5, that the capacitor in one capacitor topology for the same average voltages has to be rated higher than the one for two capacitor topologies, because it has to withstand these square voltages, which are higher than the average voltage, which we want to see in the transmission line. So it will depend on the RMS value and the voltage rating of the capacitor, depending on if we have one capacitor in the topology or two capacitors for two individual lines.
Okay.
Yeah.
Okay, thank you. Because the number of components that you use and or require for a specific topology, and the number of switches, of course, the number itself are specific to the topology, but the investment cost that one should pay to design this power flow controller topology is related to the ratings of the components, how much energy storage the capacitor should accept, or how much volt ampere ratings the components should have, right? So how would you design such a topology, I mean a PFC topology, in a cost-effective way? How would you start? Because you talk about the different components here and have a nice evaluation. What happens if, for example, one should say that we need to deploy 1,000 of these topologies in the future meshed HVDC grid?
Yeah.
How would you do that?
So if I understood you correctly, you are trying to discuss that how will we start from the scratch if someone says we need thousands
Yeah,
of
yeah.
these?
You have the topologies
Yeah.
there, and you could easily, make an evaluation of the number of
Sure.
components and everything. Number of components is fine. I mean, you need 2 capacitors, 5 switches, 5 diodes. That's okay. But then when it comes to the cost or to the investment,
Yeah.
since you talk about the per unit evaluation, per unit ratings, and so on.
So
So what kind of power is processed by these topologies? How does the load look like in the topology?
yes.
That's where I would like to start. I mean, thinking what is the mission profile basically of the topology? Because this will also define how much components or how the components operate and perform.
So first and foremost, if someone asks me to design this power flow controller, I will ask which quadrant operation they want. As we can see in figure, it was in figure 7.3a, previous figure, 1 page previous. So first I will ask them, what kind of voltage, which quadrant operation do you want? If you already have the load defined, we can choose very simple topology depending on if we need 1 quadrant operation or both the quadrant operation. And I think before making any big investment, people would like to do that. And then it can also be a choice if in which line we want to increase and decrease the current as shown in figure 7.3b. So this would be the first question I would ask. And then secondly, depending on how much voltage ripple we can withstand in the system. For example, as shown in 7.5 A and B, there is a decent difference between the voltage inserted in these 2 lines as shown by Vx and By. One has square waveforms, another one is a triangle waveform with very much lower ripple as compared to the previous one. So this could be one aspect. I mean, if we can have a ripple of 0 to, if we can have the square waveforms in the transmission line, then maybe we will need just 1 capacitor rather than 2. Here in the 2 capacitor topology, apart from the switches and 2 capacitor, we need an inductor as well, which again further will add the cost. So it depends how much you can basically withstand in terms of voltage ripple and hence the cost.
Yeah, because I think all these constraints should be included in such a optimization for designing the most cost-effective topology, right?
Yeah, and also how much loss we can withstand in the sense, if as I said, loss, what I meant is loss in terms of operating range, how much we can compromise with the operation as shown in figure 7.3. If we can just be okay with 1 quadrant operation, maybe we don't need very complicated PFC topology.
Yeah, because losses basically are translated into operating cost.
Exactly.
Like how much losses or how much electricity you basically spend to operate the PFC in the system.
Yeah.
Especially if you have several of them, not just one.
Yeah. And by the way, I got the revision for this paper last Friday,
nice.
but yeah, for the experimental part, we have already submitted the revision for the next chapter.
Yes, perfect. Yeah, I have perhaps a couple of more questions, and then I will stop. This is something you mentioned in your presentation, and that was not so clear for me. It was about on chapter 8 in your thesis, when testing the protection of the topology, of the PFC topology.
Yeah.
You talk about the inductor values that you perform evaluation for a large range from
10 to the power minus 8 to minus 2.
That's 10 nanohenry to 10 millihenry, right?
Yes. Yes.
And my question there is, how realistic is the 10 nanohenry case? I know that's a very worst case because the inductance is super low, but is it really a practical, I mean, from the practical point of view, do you really expect 10 nanohenry?
The thing is, it depends on the parasitics of the circuit. If the parasitics are in the same range, maybe they will influence this operation. And so the choice of the inductor will at the end depend on how fast your communication is and how much voltage you can withstand in the capacitor. So choosing this low value. I'm not sure how these are commercially available, but I know there are very small capacitors available for the range of nanohenry, but I'm not sure how will it be implemented in the HVDC system, but it was more like a theoretical analysis. So from the practical perspective, maybe few millihenry, maybe, but then again, if we are increasing the inductance, as I said, then we will have to design the capacitor for higher voltage, and that's like a trade-off between the capacitor rating and this inductor, and also the and then if we use a bit higher value of inductance, then we will have more time for the communication system as well, since we already designed the capacitor for the fault case.
Yeah, yes. So my very last one is basically, now you have investigated two different things, or basically three: the passive cooling, active cooling, and the PFC topologies. So how would you combine in an optimal way these three concepts? I mean, the two concepts, the passive and active, with PFC or PFC circuit. I mean, what would you use and how would you choose the best performing overcurrent mitigation approach for a PFC or an HVDC? Because that's basically one of the applications you described in the thesis.
So as we can see in the fault cases that there might be some time when the switches will have to withstand much higher currents than they are rated for. That is where the enabled power module might be put into the use. And since we are talking about the HVDC system, we may not have the limitation of the space, because if we are building maybe this big room, maybe we don't mind increasing the area by 1 meter square, for example. So for this particular application, one thing we can do is that to use a huge copper block below the chip, because we are not constrained by the space, and this has very similar performance as we saw for the top and bottom cooling. However, so since it's in the range of few milliseconds, as we have seen that microchannel cooling can actually have much longer duration if it really comes to the point, or if the cost is not a constraint and the complexity is not a constraint, then my ideal choice to do would be microchannel cooling, because it can give the best cooling performance in terms of overcurrent duration. But from practical perspective, I think implementing top cooling as a passive cooling, I mean, would be a better choice, because we definitely don't want to increase the complexity and the cost. So
top cooling, you still increase the manufacturing effort, right?
Yes, we do. We may have to design the whole power module altogether. So since you asked about the comparison of passive and active, so that's what I meant. If we really, really need overcurrent duration much longer than what we can achieve from the passive methods, then we may want to investigate microchannel cooling. But if we can achieve the similar performance with the passive cooling, either by applying a big copper block below the chip or a small block on the top, then we can probably just design that. And from my perspective, maybe it's a preferable choice, because it's a passive system. Once you have it, you have it. You don't have to maintain or turn on the pump or something.
Yeah.
So that's my point of view about it.
Yeah, thank you.
Okay.
Thank you very much. Yeah, I think I'm done.
Thank you very much. I think we keep on going immediately. That's what I would say. And then we would continue with questions from the evaluation committee, starting with Torbjörn Thiringer, who's furthest away from KTH at Chalmers.
Okay, thank you. So first, I would like to thank you for a nice thesis work on a very timely subject, and congratulations to nice experiments and a good publication record.
Thank you.
So maybe we can start with page 16 in the thesis. Maybe it's if you scroll the slides.
Okay.
I think it was You didn't put up the slide numbers on your slides,
Yeah.
but in the beginning somewhere.
Okay,
A
I
little
will.
bit down. Further. Yeah, this one it is. Slide 11.
Yeah. It is the one with the setup, I guess.
No. Okay, no.
I'm gonna move, and you can stop me when you think it's the right one. Further.
Here it is. Back one. So
Yes.
here you didn't place the microchannels in this figure. How come?
So the thing is, we didn't investigate, so it was in the beginning of my PhD, and we didn't investigate the microchannel by myself for transient applications. So that's why I didn't put it. However, from the steady state analysis of the previous research work, probably I could have at least put for the steady state, if not.
And I guess where would you place it?
I think I will place it from somewhere from milliseconds and further, because as we saw that the microchannel increased the cooling in few milliseconds, if I remember correctly. So we were able to control the. We were able to increase the overcurrent duration from, for example, 2OC from 0.75 to 3 seconds or so. So I would say from milliseconds to seconds or minute, because as you can see in the thesis on page 38, that the overcurrent duration can be increased to even more than 20 seconds, which means the devices didn't really reach their thermal limits. So we can keep on increasing until minutes as well.
Yeah, I would like to place it more to the right.
Yeah, okay.
But I think that the solid copper block will always, for a short term, be better than for millisecond range. Then Peltier elements. Did you consider it any deeper? Do you have any thoughts if it would be successful or not?
Actually, when I was doing the literature for this Peltier, I would like to show a slide where here. So this was the only application actually I found where they investigated, at least at that time when I was writing the paper, this was the only literature I found which investigated Peltier cooling on the top of the chip, and they did this investigation for steady state temperature. So, so I didn't really find it for transient application, and I didn't investigate by myself as well. But as mentioned in the literature one, there are some limitations of the Peltier element. For example, need for additional power source. Of course, it's an active cooling, so we will need. And second is the materials are more expensive than other methods. And then low thermal conductivity of conventional Peltier element puts a limitation on how much we can actually absorb. And as you can see in this diagram as well, that it has to be combined with phase change material to really get increased cooling.
Yeah, I tried it once, and one thing that but it was to cool a battery cell.
Okay.
And one thing that people never mention is that the Peltier element, you feed it with energy, and that energy becomes loss. So it was really, you really have to keep the cold side, the cooling side really cool. Otherwise, it could sometimes happen that it heated my sample instead.
Okay.
So it is, you really have to work hard on the secondary side to bring that temperature down.
That's true.
So
yeah, it might.
Peltier elements are tricky, I think.
Yeah, I think so too.
Then I had a question on Article 10.
Yeah.
If you,
I should have it.
maybe.
Yeah.
So here, you used your special setup to generate pulses. Maybe you have that picture about that pulse, that 2 milli.
Yeah.
Yeah, this is the pulse.
Yes.
Okay. The pulse had a big peak in the beginning and then during 2 milliseconds, a more stable value. Was it, how come you choose this time period around 1 to 2 milliseconds? Was that on purpose or? Otherwise, I was thinking when I started to read the thesis that it should be a longer pulse.
The reason we chose 1 millisecond pulse was that in most of the data sheets, they usually give the peak current for 1 millisecond pulse only. It's mentioned that TP is equals to 1 millisecond, and then they give the corresponding current, how much you can go. But since we usually design our electronic circuits with some safety margin, so maybe we have some margin to actually exploit the temperature margin of the device. So that was the investigation we were interested in that, okay, this is given in the data sheet, but how further we can go if we have the same duration and how much overcurrent we can withstand. So as we concluded from the investigation that few times overcurrents until 4.5 times of overcurrent, it should be okay. The device will not fail. However, there may be some changes in the electrical characteristics, but it will not fail until 4.5. So that was the main takeaway of that. And that is the reason I chose, that was the reason I chose 1 millisecond, because that's what is the limit given in the data sheet.
Okay, yeah, thank you. I was a bit wondering in a later experiment, or maybe it was earlier, you used a power supply. And then I guess you created a square pulse or?
For this one?
No, not for, it was in when you measured, for instance, the microchannel cooling. But you can say on this slide, I was just wondering, was there any thought of maybe using a square pulse from a power supply for this test, or did you really want this wave shape?
Yeah, we actually thought about that, if we should use square wave or if we should use the sinusoidal. But one thing which, due to which we thought that we can use sinusoid was about the turn off of the device. We may need a more complicated circuit to actually turn off device from current flowing. So this was much more easier as compared to turning off, as compared to the designing of circuit for turning off. So this was the reason we chose. Yeah.
Then I was a little bit interested in the temperature development during the tests.
Yeah.
And I understand how you got it, but I was also thinking, could one see that in the RDS on? That, for instance, when you are running four times over current, then you got 178 degrees. There was a table, I don't know if
it's this one, I guess.
Yeah, this one, yes.
Yeah.
And then you had the 2 times, and then you got the 64-degree temperature increase. And then I was thinking, could you see that in RDS if you divided VDS by IDS?
Yeah, I think we are
in
talking...
the article you have
a table.
You have the graphs at least.
Yes.
And I tried to look myself. But then what I could see, it was always 1 ohm. The VDS and IDS were similar in both cases, which surprised me. I would have expected a little bit higher RDS when you had the higher temperature.
Are we talking about figure 7 here or figure 4 here? Which one are we talking about?
Yeah, figure 8.
Figure 8, okay. Okay, so if...
Dimos was talking about some parasitics. I was also wondering if there is something else in the...
Yeah, I mean, I could have calculated just by dividing the data, basically. I didn't calculate it.
I tried a visual division then. I tried to do it visually, but because it was difficult with the small scaling.
Yeah, if I check the figure 7, I don't really see a huge difference, at least by using the curve tracer. But during the pulse, I could have calculated by dividing these 2 values, basically.
But I guess
But-
the temperatures are at the end of the event, or?
The temperatures are, yes, it's like the average temperature because it's a hypothetical concept of
Aha,
estimating.
it's average temperature.
Yeah, it's an average temperature for the chip. Yeah.
Then it was a bit interesting that you had such a large spread in the threshold change for 3 times overcurrent, but not for the others. That is figure 4. Did you have any idea why that was the case?
Yes, we discussed about it previously, me and my supervisor. We could see that there was some, let's say, irregularity in that sense, and one reason could be the least count of the curve tracer in terms of measurement, because these degradation should be higher when we increase the overcurrent and the number of cycles. But if we are not seeing that, I think probably the most prominent reason could be the least count of the curve tracer, because they are in the range of few volts. So
Okay.
yeah, in my opinion, it might be the curve tracer.
Okay, then I will also take a question on Article 9.
Yeah,
And it's about the component you used.
let me have
It
that.
is on
Yeah,
page
the comparison.
under table 3, where you say that you have did you do an arbitrary component because you're right, which shares similar current and voltage rating?
Are we talking about the article?
Yes.
So is it this page if we are at the same?
Yes.
Okay.
It is right under the table there.
Okay,
So you had chosen a Wolf speed MOSFET.
Okay.
And then, but it
Yes.
seems like you are not exactly using this one. You are using something similar, or?
Are you talking about how I came to that rated current value?
Yes, and especially the RDS on. Because when
yes.
I downloaded that MOSFET, it had similar current rating. That's
Yes.
correct.
Yes.
But the resistance was very different.
Yeah, so we actually kind of got the data from 2 different documents from Wolfspeed. On the first, on the right side, it's a data sheet which uses the chip CPM-M3, the number mentioned on the top. And on the left side, they gave the die area RDS on. If you want, I can zoom in, but the one marked in red has RDS on at 25. Do you see the cursor here? This one. This is the RDS on at room temperature, and then this is the die area here, and this is the blocking voltage. And then I took the current density per unit per centimeter square from this one, and I translated that current density, that amount of current, to the die in my investigation, which is 9.1 by 9.1 mm. So that's how I calculated the rated current. And then I took 60% of that rated as a safety margin. So if it was rated for 269, I took 60% of that, and which is 158 amperes approximately. So that's how I came to these numbers from.
But is this the same data sheet, this E3M0021120K?
So since I took the energy switching energies from the datasheet which you are mentioning, because this MOSFET had similar current rating as the one which we are investigating for. So it's like assuming these things, because in reality we don't have the physical device. We have to take the data from the datasheet.
In this circuit, you operated with a switching frequency of 7.5 kilohertz. But why not just run DC current instead of having a switched application if you were establishing the transient thermal behavior?
Yeah, that's true. The reason I kept switching frequency was first, initially I was comparing these silicon and silicon carbide, as we have seen in publication 2. But then I just continued the investigation for the exact same operating conditions so that I can just compare all the techniques I'm investigation. And at the end, it is the heat flux which will matter basically. So yes, you are right. We could have done that just by letting a DC current or DC current flowing through it. But in the beginning, we started with the inverter application and then DC-DC converter application, which ultimately all the analysis, all the thermal analysis will translate to, all these analysis will translate to the heat flux and thermal analysis. But yeah, we could have done that, but we just took some real life data to
Okay, yeah, that's fine. Okay,
estimate.
and one final question is table 4 in the article.
Yeah.
Those values of losses, how did you get them?
I used the application note and the methods given by Infineon and Dynex, and I just followed those techniques.
Okay,
to
so
measure.
that current 158.37 amps, is that in, that is not the DC current flowing through the, that is not the is that the current flowing through the transistor, or
Yes.
is it an average current, or what is it?
So I assumed it, let's say, so since it is being used for DC-DC converter, so it will be, so it will have the current flowing through it like square waves. And this is the current I assumed to be 158, let's say the peak in all the investigated cases.
Okay, the peak.
Yes.
Okay. Yes, then I think I leave the word over to the next person. Thank you.
Thank you
very
so much for the questions.
Answers.
Okay, thank you very much. Thanks for the invitation and the opportunity to read this very interesting work. I think you have done a great job. It's very extensive.
Thank you.
You have got lots of questions already, so I will try to keep it a bit short. But I have still a few questions. And first, I would like to talk about this overcurrent testing. This overcurrent testing, when you're performing that, was that done from room temperature device, or was it already preheated when you did this overcurrent testing?
So they were all tested at the room temperature. So I didn't even connect the heat sink because it was 1 millisecond of pulse. So no thermal modification in that sense. And we actually performed all at the room temperature. So that's why I assumed the T case here as to be, or the ambient temperature to be 25 in the calculations.
Okay, so if you consider this in an application point of view, I mean, when you having the overcurrent will happen, you will probably already having working in an operating temperature.
That's true, yes.
Do you believe that you will affect your results in some way? Because I mean, you have some energy margin to reach the nominal temperature before.
So if the device is already running, let's say if it has 100 degrees centigrade at the chip for an assumption, I mean, I'm not expecting a very high difference, or maybe there is a difference. It depends on the temperature that the die reaches and how soon. So if we are already at 100 degrees centigrade, then probably the device may even fail at 4.5 OC instead of 4.8 overcurrent. So my estimation would be that since we started at 25, so all the performances would be shifted by 75 if the device is operating at 100. So probably the failure might be a bit quicker. That's my guess.
Okay, thank you.
Yeah.
The related questions about this RDS-on measurements. Is that also room temperature measurements?
Yes.
And that corresponds to the data sheet? RDS-on values?
Yeah, they give at 25 degrees centigrade as well. Yes.
Is it similar at the elevated temperature, this behavior?
I mean, when we measured this RDS on, we tested the devices and they were basically cooled down to room temperature in some time. And then we tested the devices in curve tracer. So the measurements were done at room temperature with a small pulse given by curve tracer. So let's say without heating, if that's what you were asking.
Yeah, but you expect to have a similar behavior with reduction if it is 100 degree, or will the behavior be different at high temperature?
Okay, so you're saying if we test the devices as 25 and at 100 degrees centigrade, how the behavior would look like?
Yeah. Do you expect some difference there?
Let me think about it. It may not be that obvious for me. So if the amount of overcurrent is same in both the cases, so I would say the degradation might be higher when the device temperature is higher. So this, and we are assuming the same overcurrent and everything. So I think the device will degrade more if the temperature are higher, because they will cause more degradation in the device due to the increased temperature. Is that what you were looking for?
Okay. I'm just curious.
Okay.
If I continue with this, with the cooling perspective, and when you have this, both the phase changing material under the chip and also the micro channels under the chip, I mean, you will get a reduction in RDS on down to the main heatsink. Have you investigated how much the RDS on, no, the thermal resistance towards the heatsink? You talked about it in your presentation. That.
So are you asking the comparison of microchannel block versus the copper block?
Yes.
I mean, we can actually try to make an estimate from the thermal response. For example, if we check figure 3.4, the right column of the figures, because they are for silicon carbide. And on page 31, figure 4.3. So here, for example, if we check 3.4b, the steady state temperature with this, no, we are talking about microchannel cooling, sorry. So this microchannel cooling is, okay, let's compare the figure 5.3a and figure 4.3, 4.3c, where we have top cooling. And this is the one, so we will be comparing top cooling with microchannel and top cooling with the copper. So if we have to estimate from this that the thermal resistance of microchannel block looks smaller to me when it's applied at the top, looks smaller to me when it's applied because there is lesser temperature, the temperature is lower during the steady state with the microchannel cooling as, or it's the other way around. Let me have a look. So here in this one, it's lower than standard module for copper at the top. And here microchannel at the top, the temperature are higher. Sorry, it's the other way around. So the temperature during the steady state are lower with the copper block at the top, as seen in figure 4.3c on page 31. And the steady state temperature is higher as compared to the figure I just mentioned for microchannel block on the top. So the the thermal resistance of microchannel block seems higher because the temperature during steady state is higher with the microchannel block, if we really compare the top cooling in both the cases.
Yeah. But when you introduce this hollow and this phase changing material there, I mean, you hinder the heat down to the heatsink.
Yes.
And that is the main cooling part for the normal operation. So does that mean that you need to in somehow degrade your power converter normal operating conditions? So that it not need to operate at a bit lower power?
Regarding a big copper block below the chip and microchannel cooling below the chip, I guess you're
Yeah.
referring to.
Yes.
So if in the thesis on page 25, figure 3.4, again, the right side, because it's for silicon carbide, we can see that there is an heat spreading effect available because of the larger area available because of the chip. So the steady state temperature for this power module is less than the standard module. However, in case of microchannel, because the dimension of this block is exactly the same as the chip, and it's very small as compared to the copper block. So this is the reason that the heat spreading at the bottom may not be available that well with the microchannel block. So, in order to answer your question, the block below the chip, if it's much bigger than chip, then we may not actually degrade the device. We can even reduce the steady state temperature and hence decrease its aging or increase the lifetime. On the other hand, if the microchannel block is very small, I meant the same dimension as that of the chip, then at least in these cases, it was hindering the steady state temperature, yes. So if we have to apply, let's say, in order to conclude, if we have to apply cooling on the bottom, then we need a bigger block as compared to the cooling when we apply at the top.
Okay, thank you.
Yeah, okay.
Yeah. About this, continue with the microchannel. You have this microchannel for cooling of the overcurrent, where you have more losses compared to a normal operation, as far as I understand.
Yes, you're right, yeah.
So if the microchannel have the capability to cool better than the normal cooling path down to the main heatsink, can you rely all alone on the microchannel cooling?
Are we referring to the top side microchannel?
Not bottom side.
Bottom
cooling.
side.
Yeah.
So relying, you mean the performance of...
If the microchannel cooling should be able to cool the overcurrent,
Yes.
where you have higher power dissipation than normal operation.
Yes.
Why do you still need the normal cooling path down to the main heatsink if you have a better cooling in the microchannel?
I mean, as shown in the slides as well, if the block is the same as that of the die, I'm not really sure if it can provide any cooling in general. For example, as shown in table as well, the overcurrent duration with the bottom cooling, where I'm assuming the same size of the channel block, it's much worse than the standard module without any modification. So I don't think we will use the bottom cooling with the microchannel with a small block. If we can increase the size of this block, yes, probably it might be even better than the copper block with just a copper block. So I'm comparing copper block, big copper block, and big block of microchannel. So if I compare these two, then maybe it's comparable. But if the size of the block is same as that of the chip, then probably we won't use it because there is not much improvement with 5 microchannels and 10 microchannel. There was improvement only when the microchannel numbers were 15 and even further. So if we really have to use it below the chip with the same size as that of the chip, then it has to have basically much higher number of microchannels. But you can achieve the similar performance when you apply at the top. But then it will come up with the disadvantage that we will need a special manufacturing of those power modules.
Yeah. Final questions. You have the microchannels. You have been working with that. You also have been working with phase-changing material. Have you considered the combination of that? I mean, to having phase-changing material in the fluid form. So in principle that you pump something that is evaporating. So in principle that you're making a heat pipe solution.
So in the heat pump, as you're saying, these are two combined.
If you pump in a liquid and that is evaporating,
okay.
so that you're taking the phase-changing effect to cool it.
Okay.
I mean, that's similar as a heat pipe what they're using in the computers and so on.
Yeah, that could be an interesting. I read something about the heat part. I mean, not read, I heard this topic in one of the conferences where they probably used it for steady state. I mean, one can use any cooling method in principle as long as it can respond quickly, whether it's removing the heat by liquid flow or by the thermal conductivity of any solid. So as long, if the heat, I haven't read that much about heat pumps in detail, but if the response time is quick, then yeah, if it doesn't take much longer time to evaporate the water, then yeah, why not? It should give the similar performance as long as it can remove the heat, just like microchannels. So yeah, it depends on the response time at the end.
Okay, thank you very much.
Okay, thank you. So I'm the last one out. So first I would like to thank you for inviting me to be a part of this defense today. And then I would like to congratulate you to a really good job. I think that you have written a really nice thesis that was easy to follow and nice to read and everything like
Thanks
that.
a lot.
So, yeah. And like you said, we have already had a lot of questions today and a really long session. So I will try to keep it a little bit short and maybe to have some more broader questions now in the end. So first, if you can say, was it some result that you get out that was really surprising for you, that was not like you expected it to be?
The surprising result, one thing which I expected was different than I thought. There are two actually. So in the chapter 4 of the thesis, where I compare top, bottom, and top plus bottom, as shown in figure 4.4, my gut feeling was that for the configuration with top plus bottom, I was hoping that it would be the best because we are giving the cooling on the top and bottom. But then, to my surprise, which somehow I think I forgot, that there would be an additional thermal resistance as well in the path. So that was one thing. Second was the table in the same chapter. Okay, the table is present in the publication 3 at the end of the thesis, if you want to refer. So table 4 and 5, here we have the comparison of overcurrent duration with copper and graphite. Actually, it's there in the slide. I can show it here rather than you turning the pages. So here. So this was something, of course, it was explainable with the help of the more detailed analysis. But for the same height, I was somehow expecting the graphite to perform better because of its 4 times more thermal conductivity as compared to copper. So this was one thing. And then I was surprised that why am I not getting the higher duration? And the answer lied in the fact that it is the very low density of the graphite. It's I think, in the order of 4 times of difference. So we have the copper is, yeah, it's around 3 times as that of the, it's 3 times lesser as compared to copper. So this was something which we expect, which was the other way around, but of course it was explainable. Other thing was this curve here, I can show here. This is the curve which I showed is the system characteristic curve. Since when I was investigating the literature, all the papers almost have different HVDC systems, and hence, so they used one of those topologies which I mentioned, but I was not able to compare among them. And when I simulated all the topologies already present in the literature, I found out that this relationship is independent of topology. So, and it makes sense. I mean, as explained in the publication 5, we have these equations, and this curve is completely driven by the set of equations given in this publication. So this was something which was slightly different than we expected. And of course, it's a nice outcome that, okay, no matter which topology you choose, you are going to get the similar. Maybe the voltage inserted in these ones may look different, but the average, if we talk about, for example, here, the shape may look different, but the average will remain the same. So this was also something we came across.
Thank you. And I mean, you have a lot of different topics. If you think about how much time you spent on them, which part did you spend most time on? What was the most challenging thing that you did that in terms of time that took you the longest time to do?
I think the longest time it took for me to write my first publication, which is a review paper, and I really had to dig in the details of all the existing technologies so that I can actually compare them on apple-to-apple comparison kind of. So that took a lot of time, but in general, otherwise for the rest, once I got started, it was kind of uniformly distributed time. So yeah, I can't say which one took most of, it's mostly the literature in the beginning which takes a lot of time, and then it's about setting up simulations, and of course the experiment takes more than what you think. And yeah, designing the system, rating the system, how much voltage you need for scale down, and getting those delivered to your university, those were more time consuming in that sense.
Okay. So one final question. If you could add one more experiment to your work that you can wish for free, that you have access to all the measurements or all the equipment that you can get, what would you do then and why?
Are we talking about overcurrent here or power flow or any?
You can choose.
Okay. That's a tricky question. I can mention few. Choosing one might be a bit difficult because they are different.
Take on overcurrent, we said that.
Yeah, so if I can really choose and do the actual measurements in the lab, I would like to compare the top cooling of copper being implemented on the top and top cooling implemented by microchannel, because that will give me a very good comparison if it's worth it to have microchannel, the kind of complexity we need. Is it worth having that complexity, or we can just use a block basically, which will again need a manufacturing, but it would be much simpler as compared to the microchannels. So,
will you do the measurements in the same way, or would you choose to measure something more, maybe heat or temperature, or would you like to add something for
I mean, if it's possible, I would also love to see the reliability aspects in that. So which one is more reliable and under what conditions? So for example, for automobile, I'm not really sure if we would like to have microchannel, for example. We may want to have system which has less moving components, for example, just a couple of. Once you have it, the unreliability would come either through the vibrations of EV, for example, or because of the temperature swing or thermal stresses. However, in microchannel cooling, there would be water flowing in the channels in this case, and then it might be there might be more reliability aspects in that sense, if I really have to comment.
Okay. Thank you. I think that was...
Thank you so much. I really appreciate the questions.
Thank you very much. Now it's time to ask if somebody online, we still have 8 guests online. If somebody wants to drop a question in the chat, please do it now. Or if somebody in the audience here in the room has a question, now is the time. We can check if somebody's dropping a question online. I don't see any. If there's anything, I'm sure also Shubhangi is available by email.
Sure, anytime.
With that, I would say we give a last big applause to Shubhangi and thanks to opponent and committee for coming here. And then next step is Hansi, the committee opponent, and me. We will go discuss, and the rest we can meet in the kitchen, and then we will have lunch later. Thank you very much.
Thank you so much.
फिर मैं भी नहीं क्या मैं लेकिन मैंने 12 भी आई यार बहुत लंबा चला 20 मिनट 1:30 बज गए। अच्छा आंसर आपको सेटिस्फैक्टरी लग रहा है? बहुत जबरदस्त आपने